Welcome to this comprehensive course on data structures and algorithms. In this video, I'll guide you through some of the most essential and widely used data structures and algorithms, covering sorting techniques and much more. We'll start with foundational topics like arrays and linked lists, and gradually move on to advanced concepts like graphs and the Dijkstra algorithm. For the segment on arrays, you'll hear my own voice walking you through the concepts. The rest of the content will be explained using AI-generated voices. So, let's dive in and build a strong foundation for mastering data structures and algorithms.
An array is a type of data structure that stores a collection of elements in a contiguous block of memory, which means that the memory addresses assigned to its elements are all together in the contiguous sequence, something like this, and not scattered like this. Each element in the array is identified by an index starting from 0. Now, the first memory address of the array is known as the base address. In this example, it's 100. And the gap between the memory addresses is 4 units, which means that each element takes 4 units of memory. Also, each element of the array should be of the same size and data type. This contiguous nature of arrays makes accessing the elements very fast. We can access any element in constant time using this formula. The address of element equals base address plus index times size of each element. So let's say you want to find out the memory address of the element at 4th index. You can simply use the formula where the base address is 100, the index value is 4, and the size of each element is also 4. Calculating this will give you the memory address of the element at 4th index, ultimately getting the element at that address. Now updating any element is also very similar. First get the element's address in constant time and then assign the new value. Now the next operation is traversing the array and getting the values. So here n is the length of the array and we need to loop over the whole array once, and in each iteration print the value. Now arrays can either be static or dynamic. Static arrays have a fixed size that cannot be changed once set, while dynamic arrays can change size as needed. For now, let's consider this array to be static, with a size limit of 8. We will explore dynamic arrays in more detail later. Now the next operation is deleting the elements. So here we have a delete function with array and index to be deleted as the parameters. Now n is the length of the array, and then there is a condition that if index is less than 0 or index is greater than or equal to n, it will return the index out of bound error. Now next line of code is a loop that runs from index to n-2, and this piece of code essentially shifts all the elements that is right of the index to one element left, effectively overriding the target element. Now let's see this visually. Let's say we have to delete the element at 0th index in the array. So this function will take all the elements that are right to it and will shift one element left. Deleting the element from the front of the array is quite expensive. You have to shift all the elements to one step left. So it will be of big O of n time complexity. Now deleting the element from the end of the array takes constant time, because the loop will run only one time and will delete the element. But on an average, deleting the element from any index will take big O of n time complexity. Now the next operation is inserting the element. So here we have the function insert that takes array, index and the value as parameters. Then similarly, n is the length of the array, and then there is a condition that will check whether index is out of bound or not. Now this loop will shift all the elements from the given index to the end one step to the right to make space for the new element. And lastly, this code will add the new element to the index. Now let's see some examples visually. Let's say we have to insert the value 15 on 0th index. Then we'll have to shift all the elements to one step right to accommodate the new element. This will be of big O of n time complexity because of the shifting. Now adding an element at the end of the array is a constant time operation, because all you have to do is to find the memory address in the constant time and just assign the new value. Now inserting an element anywhere in the array will on average have a linear time complexity. Now the array is full and you cannot insert any more elements because it is static and cannot change its size. To address this limitation, computer scientists have invented the dynamic array, which can adjust its size as needed. Now let's see how a dynamic array works. Initially, suppose we have an array of size 2 with a base address of 100. Now we need to insert another element. The array becomes full and needs resizing. To handle this, a new array is initialized, usually double the size of the previous one. All the elements from the old array are then copied to the new array. The old array is deleted and the new array becomes the current array. This resizing process may repeat as needed. While resizing, we need twice the amount of memory each time to allocate the new array, resulting in a sequence like this: 2 plus 4 plus 8 and so on. And this will converge to big O of n, which would be the space complexity. Now time complexity will also be big O of n, because while resizing, we have to copy the elements from the older array to the newer one, so it will take big O of n as well. Now let's see the pseudocode for this dynamic array resizing. First, we start by initializing the array with a capacity of 2 in our example and setting the size to 0, which will increase as new elements are inserted. Now the resizing function takes the current array and its capacity as input parameters. First, it calculates a new capacity, which is twice the size of the older one. Then it creates a new array with this new capacity. Next, it copies all the elements from the old array to the new array, which requires linear time relative to the number of elements. After copying, the old array is deleted to free up the memory, and finally, the reference to the array is updated to point to the new array, and the capacity is updated to the new capacity. Now, when inserting the new element, the algorithm will first check if the array is full or not, and if full, it will first resize it, then will perform the insertion as usual. That's pretty much all about dynamic arrays. Now let's summarize all of these operations and their time complexities. First, for access and update operations, both are always constant time operations, as they involve direct indexing into the array. And traversal will always take linear time, as it requires looping through the entire array once. Now, the best case for insertion occurs when adding an element at the end of the array, which generally takes constant time, except when resizing is needed. In such cases, the insertion will take linear time due to the resizing process. But resizing is infrequent, so the process generally takes constant time. For the average and worst cases, insertion will always take linear time complexity because of the need to shift elements to accommodate newer insertions. Now, when it comes to deleting elements, the best case happens when the element to be deleted is the last one. In this scenario, the algorithm simply removes the element without shifting any others, resulting in constant time. However, in the average and worst cases, deletion will take linear time due to the need to shift elements. Now arrays can have multiple dimensions. Here we have an example of a one-dimensional array which contains base elements. Now this is a two-dimensional array which is essentially an array of arrays. So for instance, if you want to access the second element of the first subarray, you would index it like this, where 0 means the first subarray and 1 means the second element within the first subarray. And this concept can be extended to arrays with n dimensions.
A linked list is a linear data structure where elements are connected to each other using pointers or links. In this illustration, the blue circles represent nodes of the list, the arrows represent pointers, and the yellow texts represent memory addresses of those nodes. Unlike arrays, where elements need to be stored in contiguous memory locations, elements of a linked list can be allocated anywhere in memory. This flexibility allows linked lists to efficiently utilize memory by allocating space as needed, making them more dynamic and adaptable to varying storage requirements. Each node in a linked list contains the data and a pointer or a reference to the next node. This reference is simply the memory address of the next node. The first node of the list is known as the head node, and the last node of the list is known as the tail node. This specific type of linked list is known as a singly linked list because there is only one pointer per node. We will explore other types of linked lists later in the video. Now let's see the implementation of the linked list and the operations on it along with visual animations. We will use Python for this because it is an easy and beginner-friendly language. First, we will define a class called node. In the constructor, we will take data as input and initialize two members, data and the next pointer, which will be initially set to none. This structure allows us to create individual nodes that can be linked together to form our linked list. Then, we'll create the class linked list. In this class, we'll define the member variables head and tail to keep track of the first and last nodes of the list. After that, we'll define the other operations we need to manage our linked list, such as insertion and traversal. Let's first start with the traversal operation. We will define a function called traverse. Inside this function, we'll create a variable called current, initially set to the head node. We'll then run a loop with the condition, while current is not none. In each iteration of the loop, we'll print the data of the current node, and then move current one step forward by updating it to the next node. This loop will continue until current becomes none, indicating that we've reached the end of the list. And after the loop ends, it will simply print null to indicate the end of the linked list. Now let's remove these address labels to make more room on the screen. The next operation is searching for an element, which is quite similar to traversal. We'll start by defining the function with a key or target element as the input parameter. Inside the function, we'll create a variable called current, initially set to the head node. We'll run a loop with the condition while current is not none. In each iteration of the loop, we'll check if the data of the current node matches the target value. If it matches, we'll return true. If not, we'll update current to its next node and continue the loop. If the loop ends without finding the element, we'll return false. Now let's see this in animations. Let's say you want to search for the element containing the data 4. First, we'll create the current variable and start by checking its data. If the data doesn't match 4, the algorithm will move current one step forward and continue checking the next node. This process will continue until either the data matches 4 or we reach the end of the list. If we find the element, we return true. Otherwise, we return false once we have traversed the entire list. Both the traversal and search operations have linear order complexity because they both involve iterating through the list in a loop. The next operation is inserting an element at the beginning of the list. We will start by defining a function with the new data as the input parameter. Inside the function, we'll create a new node using this data. We then need to check if the head is none, which indicates whether the list is empty. If the list is empty, we'll assign both the head and tail to this new node. If the list is not empty, we'll set the next pointer of the new node to point to the current head node, and then update the head pointer to this new node. Inserting at the end is also similar. It starts with defining the function, with the new data as the input parameter. Next, it creates a new node with this data. The algorithm then checks if the list is empty. If it is, it assigns both the head and tail to this new node. If the list is not empty, it sets the next pointer of the current tail node to the new node, and then updates the tail to the new node. Both inserting at the beginning and at the end of a linked list are constant time operations because they involve only a few pointer changes. Next, we'll discuss inserting at a specific position in the list. First, we'll review the code and then look at a visual example. We'll start with defining the function, taking new data and index as input parameters. We first create the new node. The algorithm will then check if the index is 0. If it is, it will perform the insertion at the beginning operation as described earlier. If the index is not 0, we'll create a variable called current, initially set to the head node. A loop will run to traverse just before the index where the new element is to be inserted. If current becomes none while traversing, it will indicate an index out of bounds error because the desired position is beyond the end of the list. Otherwise, we update current to its next node. Once the loop ends, we update the next pointer of the new node to point to the next node of current, and then update the next pointer of current to point to the new node. Finally, we'll check if the new node is the last node. If it is, we update the tail pointer to the new node. Let's say you want to insert data at the third index. First, the algorithm will create a new node using the new data. Then, it will create a current variable starting at the head, and traverse until it reaches the node just before the target index. The algorithm will then adjust the pointers accordingly to insert the new node at the specified position. This operation takes linear time because the algorithm needs to traverse the list to reach the target index. Next is deleting from the beginning of the list. This operation will start with defining the function. The algorithm first checks if the list is empty. If it is, the function will simply return. If the list is not empty, it will check if the head and tail point to the same node, which would mean the list contains only one element. In this case, both head and tail will be set to none. If the list has more than one element, the algorithm will move the head pointer to the next element. Since we are using Python, we don't need to manually delete the first element because Python handles memory management automatically. However, in languages like C++, you would need to explicitly delete the node to free up memory. Next, let's discuss deleting a node from a specific position. We'll first look at the code and then the visuals. The process starts with defining the function, taking the index as an input parameter. The algorithm first checks if the list is empty. If it is, the function will simply return. If the index is 0, it will perform the delete from beginning operation as described earlier. If the index is not 0, the algorithm will create a current variable, initially set to the head node, and traverse the list up to the node just before the target index. After the loop ends, it will check if the current node is the tail. If it is, the tail pointer will be shifted to current. The algorithm will update the next pointer of the current node to skip the node to be deleted, pointing directly to the node after it. Since we are using Python, memory management will be handled automatically. Now let's say we want to delete the element at the third index. The algorithm will create the current variable and traverse the list until it reaches the node just before the target index. It will then update the next pointer of this current node to point to the node after the one to be deleted, effectively skipping the node at the third index. The next operation is reversing the entire list. We'll start by defining the function reverse. First, we create a variable called previous, initially set to none, and a variable called current, assigned to the head of the list. The tail will be updated to become the head. Then, while current is not none, assign next node to current.next to keep track of the next node. Then update current.next to point to previous, effectively reversing the link. Then update previous to current. And then move current to next node. The loop will continue until current becomes none. Once current becomes none, the loop will break. Finally, we will update the head to point to previous, which is now the new head of the reversed list. Reversing the entire list is a linear time operation because it involves traversing the list once. Before moving to the doubly linked list, let's summarize all the operations and their time complexities. Insertion at the beginning and end is a constant time operation because it only needs to change a couple of pointers. Inserting at a specific position takes linear time because it traverses the list up to the index. And deleting from the beginning takes constant time, while deleting from the end or any specified index takes linear time because of the traversal. And searching, traversing, and reversing all take linear time. And space complexity is constant in every operation because it does not need extra memory beyond a few pointers. Another type of linked list is a doubly linked list. In a doubly linked list, each node contains two pointers, one pointing to the next node and the other pointing to the previous node. This structure allows for bidirectional traversal of the list. The next pointer points to the memory address of the next node in the list, and the previous pointer points to the memory address of the previous node in the list. Because each node has an additional pointer compared to a singly linked list, a doubly linked list uses more memory. However, it provides the advantage of allowing traversal in both directions, which can simplify certain operations and algorithms. The implementation of the node class for a doubly linked list is similar to that of a singly linked list, with the addition of a new previous pointer. The node class will now include both next and previous pointers. The doubly linked list class similarly includes head and tail pointers, initially set to none, followed by all the operations. Now, I will not show the code for the operations, only visuals. For code, you can always do ChatGPT. To insert at the beginning of a doubly linked list, first create the new node. Then, set the next pointer of the new node to point to the current head node. Next, update the previous pointer of the current head node to point to the new node. Finally, change the head pointer to point to the new node. To insert at the end of a doubly linked list, first create the new node, and then set the next pointer of the current tail node to the new node, and set the previous pointer of the new node to the current tail node. Then, update the tail pointer to point to the new node. Both these insertion operations are a constant time operation. To insert at a specific position in a doubly linked list, such as between nodes with values 4 and 5, first, traverse the list to reach the node just before the desired position. Once you reach the correct location, create the new node with the given data. Then, update the pointers. Set the previous pointer of the new node to point to the current node, and the next pointer of the new node to point to the node next to the current. Next, update the next pointer of the current node to point to the new node, and update the previous pointer of the node that is now after the new node to point to the new node. This ensures that all links are properly adjusted to include the new node in the list. This is a linear time operation because we need to traverse the list to reach the desired position before we can perform the insertion. To delete the element from the beginning of a doubly linked list, first, get the next element of the current head node. Update the previous pointer of this next element to null. Then, set the head pointer to point to this next element. And to delete the element from the end, first, get the previous element of the current tail node. Then update the next pointer of this element to null. Then, set the tail pointer to point to this previous element. Both these operations are constant time because they involve a fixed number of pointer updates, regardless of the size of the list. To delete an element from a specific position in a doubly linked list, such as the node with the value 4, first, traverse the list to reach the node with the value 4. Once at this node, update the next pointer of its previous node to skip over the node being deleted and point to the node after it. Similarly, update the previous pointer of the node after the one being deleted to point to the previous node. This maintains the links between the remaining nodes in the list. This is a linear time operation because we need to traverse the list to reach the node at the specific position before performing the deletion. Reversing a doubly linked list is simpler than reversing a singly linked list. Here's how to do it. First, define the function for reversing the list. Create a pointer called current, initially set to the head of the list. While current is not none, swap the next and previous pointers of current. Then, update current to its previous node. Note that due to the swapping, what was previously the next pointer is now the previous pointer, represented by green color in our visuals. This process continues until current becomes none. After the loop breaks, swap the head and tail pointers to complete the reversal. The time complexities of all the operations in a doubly linked list are generally the same as in a singly linked list, except for deletion from the end. In a doubly linked list, this operation is constant time, because the second last element can be accessed from the tail node, making the deletion operation efficient. The next type of linked list is a circular linked list. In this structure, instead of the next pointer of the tail node pointing to none, it points back to the head node. This creates a circular reference, where the list forms a loop and there is no distinct end. Consequently, you can traverse the list starting from any node and eventually return to that node, making it useful for scenarios where a continuous cyclic traversal is needed. To insert a new element at the end of the list, create a new node. Then set the next pointer of the new node to point to the current head node, and update the next pointer of the tail node to point to the new node. Finally, update the tail pointer to the new node. Now, to remove the head node in a circular linked list, change the next pointer of the tail node to point to the node after the head, and move the head pointer to that node. All other operations in a circular linked list are quite similar to those in other types of linked lists. And of course, there can be variations, such as a doubly circular linked list. But I'll leave it to you to figure out the details. If you need any help with specific implementations, or have further questions, feel free to ask in the comments. A stack is a data structure that follows the last in, first out principle. This means the most recently added element is the first one to be removed. Adding elements to a stack is known as pushing, while removing elements from the stack is called popping. When you push an element onto the stack, you place it on top, making it the new top element. Conversely, when you pop an element from the stack, you remove the element from the top, effectively making the next element inline the new top. Think of it like a stack of plates. You add new plates on top, and you only remove the top plate. Now, let's say you've popped all the elements from the stack and it's empty. If you try to pop another element, you will encounter an error known as a stack underflow error. Conversely, if you attempt to add more elements than the stack's capacity allows, you will encounter a stack overflow error. A stack can be implemented using both arrays and linked lists. We'll first explore the implementation using arrays, and then we'll look at how to implement a stack with linked lists. We'll use Python for the implementation. We'll start by defining a class called stack. In the constructor, we'll set a default limit of 6 for the stack and initialize 3 members: items to store the stack elements, size to track the current number of elements, and limit to set the maximum capacity. After that, we'll define the operations such as push to add elements and pop to remove elements. To define the push operation, we'll start by creating a method called push that takes the element to be added as an input parameter. First, it checks if the stack is full by comparing the current size with the limit. If the stack is full, it will raise a stack overflow error. Otherwise, it will append the new item to the items array and increase the size by 1. To define the pop operation, we'll start by creating a method called pop. First, it checks if the stack is empty by verifying if the current size is 0. If the stack is empty, it will raise a stack underflow error. Otherwise, it will decrease the size by 1 and remove and return the last item from the items array. There's also a peek operation that returns the top element without modifying the stack. We'll start by defining the peek method. First, it checks if the stack is empty. If it is, it raises a stack underflow error. Otherwise, it simply returns the top element without removing it from the stack. Now, let's see these codes in action, along with the visual animation. First, we'll initialize the stack object using the class we defined earlier, leaving the limit set to the default of 6. This stack animation is a visual abstract representation, while the array below represents the actual implementation. After initialization, we'll push elements onto the stack. Pushing means appending elements to the array, which is a constant time operation. Then, the peek operation will simply return the top element of the stack, which corresponds to the last element of the array, also in constant time. Finally, removing an element involves deleting the last element from the array, which is another constant time operation. Next, let's explore the implementation using a linked list. If you're not familiar with how linked lists work, you might want to check out the detailed animated video linked in the description. In the linked list implementation, the top stack element corresponds to the element at the head of the list, while the bottom element is at the tail. Popping an element involves deleting the node from the beginning of the list, and pushing an element means adding a new node at the head of the list. We'll first start by defining the stack class. In the constructor, we'll set a default size of 5, though this is optional. Then, we'll initialize a linked list to store the stack elements, set the maximum size, and keep track of the current size. After that, we'll define all the stack operations, such as push, pop, and peek, to work with this linked list implementation. Let's start with the push function. First, we'll define the function and take the value to be pushed as the input parameter. Then, we'll check if the stack is full. If it is, we'll raise a stack overflow error. Otherwise, we'll insert the data at the head of the linked list and increment the current size by 1. Next, to pop an element, we will first define the pop function. Then, we'll check if the stack is empty. If it is, we'll raise a stack underflow error. Otherwise, we'll decrement the current size by 1 and delete the node from the head of the linked list. The peek operation is also similar. We'll first check if the stack is empty. If it is, we'll raise a stack underflow error. Otherwise, we'll return the data from the head node of the linked list without removing it. Now, we will first initialize an object of the stack class we defined earlier. The stack you see on the right is the abstract representation, while the linked list below, initially set to null, is the actual implementation. Pushing onto the stack corresponds to inserting elements at the head of the list, which is a constant time operation. Popping involves removing the element from the head node, which is also a constant time operation. The peek operation simply retrieves the data from the head node of the list, and this too is a constant time operation. Understanding the linked list data structure is crucial to grasp how this implementation works. We have detailed videos on both linked lists and arrays on this channel, which you can check out for a deeper understanding. Now, let's look at a use case of the stack data structure. Imagine you're editing an image in software. First, you erase something in the image, then you paint something, and then you paint again. These actions are stored on a stack. If you want to undo these changes, the software will simply pop those operations off the stack. This allows you to reverse your actions in the exact order you performed them, demonstrating how stacks are used in real-world applications like undo functionalities in software. A queue is an abstract data type, where elements are inserted from one side, known as the rear or back, and are removed from the opposite side, called the front. It operates on the first in, first out principle. You can think of it like a queue at a market checkout. The person who arrives first will be served first. Queues can be implemented using both linked lists and arrays. First, let's look at the linked list implementation. A solid understanding of linked lists is necessary to grasp this concept fully. If you're not familiar with linked lists, we have a detailed video on the topic available on our channel. You can find the link in the description. In a linked list implementation of a queue, inserting elements at the back of the queue, known as in queue, involves adding to the end of the list. This operation is performed in constant time. Conversely, removing elements from the front of the queue, known as dequeue, involves deleting from the head node of the list, which is also a constant time operation. Let's see the code for implementing a queue using a linked list. First, we define the queue class. In the constructor, we initialize the queue using the linked list class that we covered in our linked list video. Next is the unqueue operation, which involves inserting elements at the end of the list in constant time. The dequeue operation first checks if the list is empty. If it is, the method will print a message and return none. If the list is not empty, it will remove and return the element at the head of the list. This is also a constant time operation. Finally, the peek operation is similar to dequeue, but instead of removing the front element, it returns the front element without removing it from the list. When we create an object using the queue class, it initializes a linked list with no elements, as shown below. The abstract representation of the queue is shown above. It will then perform operations accordingly. Next, let's look at the implementation using arrays. First, we'll consider the naive approach. In this case, unqueuing means appending elements to the end of the array, which is a constant time operation. However, dequeuing involves removing the element from the first position. This operation is a linear time process due to the need to shift all subsequent elements to fill the gap. Can we do better? To make the dequeue operation more efficient, we can initialize a front pointer at the 0th index. Onqueuing will remain the same as before, where we append elements to the end of the array. However, when performing the dequeue, instead of shifting all the elements, we can simply set the element at the front pointer to none and move the front pointer one index to the right. This way, the dequeue operation can be performed in constant time. But there's a problem. Although the dequeue operation now takes constant time, the issue arises when the array becomes filled. The memory space to the left of the front pointer is wasted, as those slots are no longer usable for new elements. To fix that issue, the circular queue comes to the rescue. In this implementation, we initialize two pointers, front and back. Initially, neither pointer is set to any index in the array. When unqueuing the first element, both pointers move to the 0th index. For subsequent onqueuing operations, the front pointer remains in place. while the back pointer moves to the next index as new elements are appended. When dequeuing, the element at the front index is assigned to none, and the front pointer moves one step to the right. Setting the element to none is optional since it will be updated later, but it's generally considered good practice to avoid confusion. The real benefit of a circular queue becomes apparent when the back pointer reaches the end of the array. When this happens, instead of stopping or wasting space, the back pointer wraps around to the beginning of the array and continues enqueuing elements in the available space. And when the back pointer reaches the position just before the front pointer, that's when the queue is considered full. At this point, there is no more room to insert new elements because the next position for the back pointer would overwrite the element at the front. In the coding part, we'll begin by defining the circular queue class. Inside the constructor of this class, we will first take the size of the queue as an input parameter. This size will determine the capacity of our queue and how many elements it can hold at most. Next, we'll initialize the members of the class. First, we'll store the size of the queue as a class attribute. Then, we'll create an array of the same size, initially filled with none to represent an empty queue. Finally, we'll initialize the front and back pointers. Both of these pointers will be set to -1 initially. This indicates that the queue is empty, as no elements have been enqueued yet. Next, we'll create a function that returns true if the array is full and false if it is not. To visualize this, imagine a queue with a size of 6. If the back pointer is at index 1 and the front pointer is at index 2, the queue is considered full. Using these values in the formula will return true. Conversely, if the back pointer is at index 0, the same formula will return false, indicating that the queue is not full. Next, we'll implement a function to check if the queue is empty. This function will simply check if the front pointer is -1. If the front pointer is -1, it means the queue is empty. Otherwise, the queue is not empty. After implementing this function, we'll define all the other methods required for the circular queue operations. The onQueue method takes a value as an input parameter. It first checks if the queue is full using the previously defined function. If the queue is full, it will print a message and return. Next, the method checks if the queue is empty. If it is, it assigns the front pointer to the 0th index. It then moves the back pointer to the index determined by the formula we discussed earlier, which gives the current position for the back pointer. Finally, the method assigns the value to the desired index in the array. The dequeue method similarly checks if the queue is empty. If it is, it prints a message and returns none. Otherwise, it creates a variable to store the value at the front index. It then updates the value at the front index to none, which is optional but generally considered good practice. Next, it checks if both pointers are equal, meaning they are both at the 0th index. If they are, it initializes both pointers to -1. If not, the front pointer is updated according to the formula we discussed earlier. Finally, the method returns the value that was stored in the variable. The display method first checks if the queue is empty. If it is, it prints a message and returns. If not, it checks if the back pointer has a higher or equal value compared to the front pointer. If it does, it returns all the elements from the front to the back in the same order. If the back pointer is lower, it retrieves elements from the front pointer to the end of the array, then takes elements from the beginning of the array to the back pointer and concatenates them. Although there are no visible loops in this code, this operation has linear time complexity because slicing the arrays takes linear time at a low level. Creating an object with that circular queue class will initialize an array along with the pointers as shown below, and the abstract representation of the queue is, as usual, above. The operations will go like this. A circular queue can also be implemented using a dynamic array instead of a static one. In this case, if the queue becomes full, a new array will be initialized, typically twice the size of the original. All the elements will then be copied from the old array in a specific order, first from the front to the end, and then from the beginning to the back element. The front pointer will be assigned to the beginning, and the back pointer will be assigned to the last element. The old array will then be removed, and this new array will become the queue. The code for the dynamic array implementation is similar to the previous one, with a key addition in the constructor, a count attribute that keeps track of the number of elements in the queue. The new function, called resize, handles resizing the array when the queue becomes full. It starts by defining the resize method, where a new array is initialized with twice the size of the original. The method then loops over the elements, copying them from the old array to the new one in the correct order. After that, it updates the parameters accordingly. When performing the onQueue operation, the algorithm first checks if the array is full. If it is, the array is resized before proceeding. Once the resizing is complete, the onQueue logic is executed as before, adding the new element to the queue. Now that was a simple queue. Another type of queue is a doubly ended queue, where elements can be inserted from either the front or the back. And they can also be removed from either the front or the back. The simplest way to implement a doubly ended queue is by using a doubly linked list. Enqueuing from the front side of the queue means inserting an element at the head of the linked list, while enqueuing from the back side involves inserting the element at the end of the list. Both operations are performed in constant time. Dequeuing from the front means deleting the element from the beginning of the list, and dequeuing from the back involves deleting the element at the tail node of the list. Both of these operations are also performed in constant time when using a doubly linked list. Another way to implement a doubly ended queue is by using an array in a circular manner. Enqueuing at the rear works the same way as before. However, enqueuing at the front means adding the element at the position just before the front pointer, taking into account the circular nature of the array, where the position wraps around if necessary. Dequeuing from either the back or the front involves moving one index before, also considering the circular nature of the array. All these operations take constant time. Think of the array like a circle, where the last index is connected back to the first index. First, adding at the back means adding at the 0th index and moving both front and back pointer to that index. Then adding at the back of the queue means inserting at the back and moving the back pointer forward. Enqueuing at the front is like moving in the opposite direction. You add an element just before the current front pointer, accounting for wrapping around if needed. Dequeuing from either end involves moving one step backward in the respective direction. From the front, you move forward one step to remove an element, and from the back, you move backward one step to remove an element. Note that the underlying memory structure is not circular at all. This analogy is just to explain the concept. The next type of queue is a priority queue, which is interesting because it operates on priority rather than just timing. Elements are inserted into the queue and arranged in a specific order based on their priority. When dequeuing, the element with the highest priority is removed first. Think of it like a hospital queue. A person with a sudden heart attack has a higher priority than someone with a mild fever. The implementation of a priority queue is complex and deserves its own video. We'll explore it further when we discuss the heap data structure. A tree is a data structure that simulates a hierarchical relationship among elements. Unlike linear structures such as arrays or linked lists, trees are nonlinear data structures that organize data in a branching format. Each element in a tree is called a node, with the topmost node known as the root. The root is connected to other nodes through edges, representing parent-child relationships. The root node is the starting point of the tree, and each node can have 0 or more child nodes. Nodes with no children are called leaf nodes. A tree also cannot have cycles. For example, an edge like this is not allowed. The tree also has a height, which is the number of edges between the root node and the lowest leaf node. In this case, since all leaf nodes are at the same level, the height would be 3. This example tree is a binary tree, which is one of the most common types of trees in computer science, where each node has at most 2 children, called the left and right child. The specific type of binary tree that is the subject of this video is a binary search tree. In a binary search tree, the value of every node in the left subtree of a given node must be less than the value of that node, and the value of every node in the right subtree must be greater. This rule must hold true for all nodes in the tree, ensuring that the binary search tree property is consistent across the entire structure. This property can be beneficial for efficiently searching, deleting, and inserting elements. Before we get into the operations, it's important to understand the concept of a balanced tree and how it impacts the tree's height. A balanced tree is one where the height difference between the left and right subtrees of every node is at most 1. If any node has subtrees where this difference is more than 1, the tree becomes unbalanced. This tree is an example of a balanced tree because every subtree of any node has equal height. Now, if we remove some of these leaf nodes, the tree will still be balanced because the height difference between the subtrees is still no more than 1. However, if we remove these specific nodes, the height difference becomes more than 1, making the tree unbalanced. In the worst-case scenario, a completely unbalanced tree will look like this, skewed or even zigzagging, resulting in inefficient operations. Now, let's calculate the height of a completely balanced binary tree, assuming the total number of nodes is n. At the first level, there is only the root node. At the second level, there are 2 nodes, at the third level, 4 nodes, and so on, up to 2 to the power h, where h is the height of the tree. If we sum up all these nodes, we get a total of n nodes. If you know a little bit of mathematics, you can solve for h, which turns out to be log n. However, in the worst-case scenario, if the tree is completely unbalanced, the height becomes comparable to the total number of nodes, n. As the tree goes from balanced to unbalanced, the height increases from log n to n. This change in height directly impacts the efficiency of operations, making them slower as the tree becomes more unbalanced. To implement this tree, we'll start by creating a node class. In the constructor, we'll take the key as an input parameter. Then we'll initialize 3 members. Left, this will point to the left child node of the current node, initially set to none. Right, this will point to the right child node of the current node, also initially set to none. Val, this member will store the value of the node, which is assigned to the key provided during the node's creation. Next, we'll initialize the binary search tree, or BST class. In the constructor, we'll initialize the root of the tree, which will be set to none initially, indicating that the tree is empty. After that, we'll define the operations that can be performed on the tree, such as insertion, searching, and deletion. Let's first start with the search operation in our binary search tree class. This is the public method that initiates the search operation. It takes the key we want to find as an argument and calls the internal helper method _search, starting the search from the root of the tree. This is the internal recursive method that does the actual searching. It takes the current node and the key as arguments. First, we have the base case. If the current node is none, it means we've reached a point where the key can't be found in the tree, so the method returns false. Then, the other base case. If the value of the current node matches the key, it means we've found the key in the tree, so the method returns true. If the key is less than the value of the current node, it means the key, if it exists, must be in the left subtree. The method then recursively calls _search on the left child of the current node. If the key is greater than the value of the current node, the method recursively calls _search on the right child, as the key must be in the right subtree if it exists. This might not be entirely clear through explanation alone, so let's visualize it to understand the process better. To search for an element, such as 4, in a binary search tree using recursion, the algorithm starts at the root node and utilizes the recursion stack to manage function calls. It first compares the target value with the current node's value. The target is less than the current value node, so it recursively searches the left subtree. If the target is greater, it searches the right subtree. Each recursive call is pushed onto the stack. And when the target is found, the function returns true. As the recursion unwinds, each function call returns true, propagating this result up through the stack. The final result, true, indicates that the target value exists in the tree. The time complexity of searching for an element in a binary search tree is proportional to the height of the tree, as this determines the number of recursive searches required. Similarly, the space complexity is proportional to the height of the tree due to the space needed to store function calls in the recursion stack. In a balanced tree, the height is logarithmic relative to the number of nodes, so both time and space complexities are big O of log n. However, in the worst-case scenario where the tree is unbalanced, the height of the tree is comparable to the number of nodes, leading to both time and space complexities degrading to big O of n. That was the recursive approach. The same thing can also be done in an iterative manner. To search for a key in a binary search tree, BST, using an iterative approach, you start by defining a search method that takes the key as a parameter. Initialize a variable current and set it to the root node of the tree. Use a while loop that continues until current is none. Inside the loop, check if the key is equal to the value of the current node. If it is, return true, indicating that the key is found. If the key is less than the current value, move current to its left child node. Otherwise, move current to its right child node. After the loop ends, if the key is not found, return false. Let's visualize the iterative search for the value 4. First, the algorithm checks the root element's value. The root's value is greater than 4. The algorithm moves to the left child in the next iteration. It checks the value again. It's still greater than 4. It continues moving left. Now that the current node's value is less than 4, the algorithm shifts to the right child. Once the match is found, the loop breaks and returns true. The time complexity remains the same as before, proportional to the height of the tree. However, the space complexity is improved to constant time, as the iterative approach only requires space for a few variables, unlike the recursive approach which needs additional space to store function calls on the stack. The next operation to consider is insertion. Let's first explore the recursive approach. First, we define the insert method. This method begins by checking if the tree's root is none. If the root is none, it means the tree is empty, so we create a new node with the given key and set it as the root. If the root already exists, the insert method calls a helper function, _insert, passing the root node and the key to be inserted. The _insert method is responsible for finding the correct position for the new key. If the key is less than the current node's value, the algorithm checks if the left child of the current node is none. If it is none, it means the correct position for the new key has been found, so a new node with the key is created and set as the left child. If the left child is not none, the _insert method is called recursively on the left child to continue searching for the correct position. If the key is greater than the current node's value, the process is similar but occurs on the right side. The algorithm checks if the right child is none. If it is, a new node with the key is created and set as the right child. If not, the underscore insert method is called recursively on the right child to continue the search. Else, if the value to be inserted is already present, the algorithm just returns. Next, let's visualize this process. Imagine we're inserting the value 11 into the tree. The algorithm will begin at the root node and compare the value 11 with the root's value. Since 11 is greater than the root's value, the recursion will move to the right child. Now this node's value is greater than 11, so the algorithm will move to the left child. The left child's value is also greater than 11, so the algorithm will move to the left again. At this point, the left child is empty, so the algorithm will assign the left child to a new node with the value 11, and then the recursion will return. The time and space complexity for the insertion operation are the same as for the search operation. Both are proportional to the height of the tree. The same operation can also be implemented iteratively. First, we'll start by defining the insert method. In this method, if the tree is empty, we'll create a new root node with the key value. If the tree already has nodes, we will initialize a variable called current and set it to the root of the tree. Then, we enter a while loop that will run indefinitely until we find the correct spot for the new node. Inside the loop, we compare the key value with the current node's value. If the key is less than the current node's value, we check if there is a left child. If there isn't, we create a new node with the key value and assign it as the left child. If there is a left child, we move the current pointer to the left child and continue the comparison. Similarly, if the key is greater than the current node's value, we check the right child. If the right child is empty, we create a new node with the key value and assign it as the right child. If there is a right child, we move the current pointer to the right child and continue the comparison. Finally, if the key equals the current node's value, we simply return without inserting a duplicate. This ensures that the new node is placed in the correct position in the tree while maintaining the binary search tree's properties. Now let's visualize inserting the value 11 using the iterative method. The process begins by creating a current variable, initially set to the root node. The algorithm will then traverse the tree by comparing the value 11 with the values of each node it encounters. Since 11 is greater than the root node's value, it moves to the right child. Then, as 11 is less than the next node's value, it moves to the left. Finally, it reaches a node with an empty left child, where it inserts the new node with the value 11. The time complexity here is proportional to the height of the tree, just like the recursive approach, as the algorithm needs to traverse from the root to the target position. However, the space complexity is constant, because unlike the recursive method, the iterative version doesn't require additional memory for function calls, just a few pointers to keep track of the current node during traversal. This makes the iterative approach more memory efficient in some cases. Before moving on to the delete operation, it's important to understand the min-value node function. This function is crucial when deleting nodes, particularly when dealing with nodes that have two children. The min-value node function takes a node as an input parameter and aims to find the node with the minimum value in a given subtree. It starts by creating a current variable, initially set to the input node. Then it enters a while loop, which continues as long as the current dot left is not none. Inside the loop, the current variable gets updated to the left child of the current node. This process effectively traverses the left side of the tree, and since the smallest value in a binary search tree is always the leftmost node, the function returns the leftmost node of the subtree. Let's break down how the delete method works in multiple steps. The process begins with the delete function, which takes the key to be deleted and calls the helper function _delete node, starting from the root node of the tree. The goal is to traverse the tree and locate the node containing the key. If the node is none, it means the key does not exist in the tree, and the function simply returns none, stopping further execution. If the key is smaller than the current node's value, the algorithm continues searching in the left subtree. It calls _delete node recursively on the left child, setting node.left to the result. On the other hand, if the key is greater than the current node's value, the search moves to the right subtree, where the function is similarly called on the right child by setting node.write to the result. This ensures the algorithm finds the node containing the key. Once the key is found, the deletion occurs, which varies depending on the structure of the node. If the node to be deleted has no left child, it returns the right child, essentially replacing the node with its right subtree. If the node has no right child, it returns the left child, removing the node and replacing it with its left subtree. For the case where the node to be deleted has two children, the algorithm needs to find the in-order successor, which is the smallest node in the right subtree. It uses the helper function, _min_value node, to find this smallest node. The current node's value is updated to the successor's value, and then the algorithm deletes the in-order successor from the right subtree to avoid having duplicate values in the tree. This maintains the binary search tree property, ensuring all nodes to the left are smaller and all nodes to the right are larger. Finally, the function returns the updated node, maintaining the tree structure even after the deletion. This approach guarantees that the binary search tree remains valid and balanced after a node is removed. Let's visualize the delete operation with animations. Suppose we need to delete the node with the value 11. The algorithm will begin at the root node and compare the key with the current node's value. It will recursively traverse through the tree, moving either left or right, depending on whether the target value is smaller or larger than the current node. In this case, the target element 11 is a leaf node, meaning it has no children. Once the algorithm finds the node, it will simply remove it by setting the parent node's reference to none. Since it's a leaf node, there's no need to restructure the tree further, and the recursion will return, confirming the deletion. The tree will be updated with 11 removed, maintaining the overall structure. Now, let's visualize deleting the node with the value 12. The algorithm will start at the root and, as usual, traverse the tree by recursively comparing the target value with the current node, moving left or right based on whether the target is smaller or larger. In this case, the node with the value 12 has one child. Upon reaching the target node, the algorithm will not simply delete it as in the case of a leaf node. Instead, it will update the parent node's pointer to point to the child of the node being deleted. This effectively bypasses the deleted node and connects its parent to its only child, maintaining the tree's structure. The recursion will then return, finalizing the deletion process. Now, let's add some nodes and try to delete a node that has two children. We'll go with deleting the node with the value 5. The algorithm will first traverse to the target node recursively. Upon reaching the node with the value 5, it will identify that this node has two children. To handle this, the algorithm will use the _min_value node function we defined earlier. It will start by looking at the right child of the target node and iteratively find the smallest value node in the right subtree. Once the smallest node is found, the algorithm will update the value of the target node to this smallest node's value. Finally, it will proceed to delete the smallest node, which will either be a leaf or have at most one child, simplifying the deletion process. Once the smallest node is removed, the recursion will return, and the deletion operation is complete. For one last example, let's delete the root node. The algorithm will begin at the root, which is also the target element for deletion. Since the root has two children, the algorithm will need to find the smallest node in the right subtree, following the same process as before. Once the smallest node is located, its value will replace the value of the root node. Next, the algorithm will proceed to delete the smallest node from the right subtree. In this case, the smallest node has one child, so the algorithm will update the pointer of its parent node to point directly to the smallest node's child, effectively removing the smallest node from the tree. This completes the deletion process, with the root node's value replaced and the tree structure updated accordingly. The time and space complexity for this recursive approach is proportional to the height of the tree, which depends on whether the tree is balanced or not. Now let's see the iterative delete method. This method uses a loop to delete a node with a given key from the binary search tree while maintaining the tree's structure. The process involves several steps depending on the position of the node and how many children it has. The method starts by setting two variables: current, which starts at the root of the tree, and parent, initially set to none. These variables help track the node we are trying to delete and its parent during the traversal. First, the algorithm searches for the node with the key to be deleted. It uses a while loop to traverse the tree. The parent variable is set to the current. If the key is smaller than the current node's value, it moves to the left child. If the key is larger than the current node's value, it moves to the right child. If the current is none, it returns none. Once the node is found, the method handles three possible cases. Case 1. The node has no children, meaning it's a leaf node. In this case, if the node is the root of the tree is set to none, making the tree empty. If the node is a left child of its parent, the parent's left reference is set to none. If the node is a right child of its parent, the parent's right reference is set to none. Case 2. The node has one child. This could either be a left child or a right child. If the node only has a right child, the method bypasses the node and links the parent directly to the node's right child. If the node only has a left child, the method links the parent directly to the left child. This effectively removes the node while preserving the connection to its child. Case 3. The node has two children. In this case, we need to find the smallest node in the right subtree, known as the in-order successor. We do this using the _min_value node method. The value of the in-order successor is stored, then we recursively delete the successor node. After that, the value of the node to be deleted is replaced with the value of the successor. This ensures that the tree remains a valid binary search tree. Now, imagine deleting the node with the value 12 from this tree. The algorithm will first iteratively traverse the tree to find the target node, which is 12. Once the target is found, the algorithm will evaluate the cases to determine how to proceed with the deletion. In this case, the node 12 has a single child, which is 13. The parent of 12 will then be directly connected to 13, bypassing 12. This effectively removes 12 from the tree while keeping the child node in place. The time complexity in this case is also proportional to the height of the tree. However, the space complexity is now constant, because the iterative method only requires a fixed amount of memory to store a few pointers, such as current and parent, during traversal. Now let's move on to the operation of getting the height of the tree. In this case, we'll only focus on the recursive approach, as it is typically done using recursion. Here's how it works. First, the public function will be called, which serves as an entry point. This function doesn't do any computation itself. Instead, it calls the helper function, passing the root node as the input parameter. Then inside the helper function, the algorithm will check if the current node is none, which means we've reached the end of a branch, so the height at this point is 0. Then it will recursively calculate the height of the left and right subtrees. The function will continue this process until it reaches the leaf nodes, and for each node, it will return the maximum of the left and right subtree heights plus 1. This ensures that the height of the tree is properly calculated by comparing the depth of each branch. This process will eventually return the overall height of the tree. The algorithm for calculating the height of the tree starts at the root node. From there, it recursively traverses the left subtree first. It continues to move left until it reaches a leaf node. Upon reaching a leaf node, the base case of the recursion is triggered, and the function returns 0, indicating the height of a leaf node. After returning from the left leaf node, the algorithm moves to the right unvisited node. If this is also a leaf node, it again returns 0. At this point, the algorithm is back at the parent node, and it calculates the height by taking the maximum of the left and right subtree heights, which are both 0. Adding 1 for the current node, the function returns a height of 1 for this subtree. The same steps are followed as the function moves up the tree, calculating the height for each node. For every node, the maximum of the left and right subtree heights is taken, and 1 is added to account for the current node. Once the algorithm finishes calculating the height of the left subtree, it moves to the right subtree and follows the same recursive steps. It traverses down the right subtree, reaching the leaf nodes, and returns 0 upon hitting the base case. For each node in the right subtree, the algorithm calculates the height by taking the maximum of the left and right subtree heights and adding 1 for the current node. This process continues recursively until the algorithm has traversed and calculated the height for all nodes in the right subtree. Finally, when both the left and right subtree heights are known, the algorithm returns to the root node and computes the overall height of the tree by taking the maximum of the left and right subtree heights and adding 1. This gives the total height of the entire tree. In this case, the time complexity would be big O of n, since it traverses the entire tree. However, the space complexity of this operation is still proportional to the height of the tree, because the recursion stack only holds information about the current path from the root to a leaf node at any given time. This path's length is equal to the height of the tree, not the total number of nodes. Let's talk about traversing the tree. In this code, the public preorder function first calls the inner underscore preorder function, taking the root node as the input parameter. The print statement at the end of the public function is there to create a new line after the traversal completes, ensuring clean output formatting. Now, inside the helper function, the first step is to check for the base case. If the node is none, meaning we've reached the end of a branch, the function will return and stop further execution. If the node is not none, the function will print the value of the current node to represent visiting that node. Recursively, move to the left subtree, calling on the left child. After the left subtree is fully traversed, it will recursively move to the right subtree, calling the function on the right child. This method ensures that each node is visited in preorder, node first, then left, then right. Let's see this visually. First, the algorithm will start at the root node and print its value. Then, it will recursively traverse down the left subtree, printing the values of the left child nodes as it visits them in preorder, node first, then left child, followed by right child. Once it has fully explored the left side of the tree, the algorithm will backtrack and move to the right subtree, following the same preorder process by visiting and printing the right child nodes. This ensures that the traversal visits nodes in a root, left, right sequence, covering all nodes in the tree. Next is the in-order traversal, which is similar to the previous pre-order traversal, except that it first traverses the left subtree before visiting the current node. In this method, the algorithm will first recursively explore the left side of the tree until it reaches the leftmost node, then it will print the value of the node. After printing, the algorithm will move to the right subtree, following the same pattern. This traversal follows the left, root, right order, ensuring that the nodes are visited in ascending order. Let's see this visually. The algorithm will start at the root node and will recursively traverse the left subtree until it reaches the leftmost node. At this leftmost node, it will print the node's value. After printing, it will then move to the right node of the current node and continue this process. The algorithm ensures that all nodes are visited in the left, root, right order, printing the values in ascending order. Next is the post-order traversal. In this method, the algorithm first recursively explores the left subtree of the tree until it reaches the leftmost node. It then proceeds to print the value of the leftmost node. After finishing with the left subtree, the algorithm moves to the right subtree of the current node and follows the same process, recursively traversing the right subtree until reaching the rightmost node and printing its value. This traversal follows the left-right root order, ensuring that the nodes are visited after both their left and right subtrees have been fully explored. Let's see this visually. The algorithm starts at the root node and first recursively traverses the left subtree until it reaches the leftmost node. At this leftmost node, it prints the node's value. After printing the leftmost node, it then backtracks to the parent node and moves to the right subtree, repeating the process, traversing recursively to the rightmost node and printing its value. Finally, after exploring both left and right subtrees, the algorithm prints the value of the current node. This ensures that all nodes are visited in the left-right root order, with values printed in post-order traversal. For all three traversal methods, pre-order, in-order, and post-order, the time complexity is big O of n, where n is the number of nodes in the tree. The space complexity for these recursive methods depends on the height of the tree. For recursive calls stack, in the previous video, we explored how a balanced binary search tree has a minimum height of log n. However, as the tree becomes unbalanced, its height can approach n, which can significantly degrade the efficiency of key operations like insertion, deletion, and search. This raises a crucial question. Is there a way to keep the tree always balanced to maintain optimal performance? This is where AVL trees come into play. An AVL tree is a self-balancing binary search tree that automatically maintains its balance to ensure that operations remain efficient. To understand how AVL trees maintain their balance, we first need to introduce the concept of the balance factor. The balance factor of a node is the difference between the heights of its left and right subtrees. Let's take a closer look at this with an example. Suppose we have a tree where the root node has two children. The balance factor of the root node in this tree is 0, because the heights of both its left and right subtrees are the same. In this case, the node is balanced. Now consider the left child of the root. The left subtree is taller by 1 level compared to the right subtree. That means the balance factor is 1. This node is also balanced. Next, let's examine the right child of the root. The right subtree is taller than the left subtree by 1 level, so the balance factor is -1. This node is also balanced. However, problems arise when the absolute value of the balance factor of any node becomes greater than 1. In other words, if the balance factor is either more than 1 or less than -1, the node becomes unbalanced. When this happens, the AVL tree performs rotations to restore balance. Before we dive into rotations and their types, let's first go over the code for the node and tree structure in an AVL tree. In the node class, the constructor takes a value as an input parameter. This value is stored in a member called value. Just like in a regular binary search tree, there are also left and right members that point to the node's left and right subtrees. What's unique about the AVL tree is the height attribute. This attribute keeps track of the height of the node, and it's crucial for maintaining the tree's balance. Unlike a normal binary search tree, where we don't worry about balance directly, the AVL tree uses this height to ensure that the tree stays balanced at all times. In the AVL tree class, we'll start by defining the root of the tree, which is initially set to none. Next, we'll define two important methods, height and getBalanceFactor. The height method is straightforward. It simply returns the height of a given node. The algorithm first checks if the node is none. If it is, it returns 0, indicating that a non-existent node has a height of 0. Otherwise, it returns the actual height of the node. The getBalanceFactor method works similarly. It checks if the node is none, and if so, it returns 0. Otherwise, it calculates the balance factor by taking the difference in height between the node's left and right subtrees. These methods are crucial as they help determine if the tree needs to be rebalanced. In addition to these, we'll also have other methods like insertion and deletion, which we'll discuss later. These methods will rely on the height and balance factor to ensure the tree remains balanced after every operation. Now, coming back to rotations, there are a total of 4 ways a node can become unbalanced, depending on its balance factor and the balance factor of its child. The first case we'll look at is the left-left LL case. This occurs when the balance factor of the unbalanced node is greater than 1, meaning it's left-heavy, and the balance factor of its left child is greater than or equal to 0. In this tree example, the balance factor of the root node is 2, which means the node is unbalanced on the left side. The balance factor of its left child is 1, indicating that this is a left-left case. To balance the tree in this scenario, we need to perform a right rotation on the unbalanced node. After rotating, the left child becomes the new root node, and the original root moves down to become the right child of the new root. This rotation effectively redistributes the nodes, making the tree more balanced. Now, the balance factor of the new root node is 0, indicating that the tree has been successfully balanced. Now, let's go back and add a right grandchild to see the general left-left case in action, along with the code. Initially, the balance factor of the root node is still 2, indicating that it's left-heavy. The balance factor of its left child is now 0, which means this is still a left-left LL case, but in a more general form. Let's break down the code for this rotation. The method takes a node as input. Here, we'll use the root node, which we'll call Z. Next, we set Y to the left child of Z, and T3 is set to the right child of Y. In the previous example, this T3 was none. Now, we proceed with the right rotation. The right child of Y is assigned to Z, and T3 becomes the left child of Z. This rearranges the nodes, effectively rotating them to the right. After the rotation, we update the heights of Z and Y to reflect the new structure. Finally, Y becomes the new root of this subtree, completing the right rotation. This operation balances the tree by shifting nodes in the right direction, ensuring that the height difference between the left and right subtrees is minimized. Now the next case is the right-right, RR, case. This occurs when the balance factor of a node is less than -1, indicating that the node is unbalanced on the right side, and the balance factor of its right child is less than or equal to 0. To balance the tree in this situation, we perform a left rotation. Let's go through this with an example. Suppose we have a root node with a balance factor of -2, showing that it's right-heavy. Its right child has a balance factor of -1, confirming the right-right case. To balance this, we'll perform a left rotation on the unbalanced node. This will essentially make the right child the new root node, and the old root will become the left child of the new root. Now, let's add a left grandchild to make it more general. The balance factor of the root is still -2, and the balance factor of the right child is now 0, indicating that it is still the right-right case, but in a more general form. Now, let's look at how the code handles this rotation. The method takes the unbalanced node as input, which we'll call Z in this example. We set Y to the right child of Z and T2 to the left child of Y. In the previous case, T2 was none. Next, we perform the left rotation. The left child of Y is set to Z, and T2 becomes the right child of Z. This rearranges the nodes in a leftward direction, balancing the tree. After the rotation, we update the heights of Z and Y to reflect the new structure. Now, the balance factor of the new root should be within the acceptable range of -1, 0, or 1, indicating that the tree is balanced again. Now, The next case is the left-right LR case. This occurs when the balance factor of a node is greater than 1, indicating that it's unbalanced on the left side, but the balance factor of its left child is less than 0, meaning the left subtree's right side is heavy. In this scenario, we need to perform a left-right rotation to balance the tree. The left-right rotation is a two-step process. First, we perform a left rotation on the left child of the unbalanced node, converting the problem into a simpler left-left LL case. After this, we perform a right rotation on the original unbalanced node to balance the tree completely. Let's break this down with an example. Suppose we have a root node with a balance factor of 2, making it left-heavy. However, the left child has a balance factor of -1, indicating that its right subtree is heavier. To fix this imbalance, we first perform a left rotation on the left child, which shifts the right heavy subtree into a more balanced form. Now, the tree is in a left-left configuration. In the second step, we perform a right rotation on the original unbalanced node. This rotation adjusts the positions of the nodes, making the left-heavy node the new root and balancing the tree. Now, the next case is the right-left RL case. This occurs when the balance factor of a node is less than -1, indicating that it's unbalanced on the right side, but the balance factor of its right child is greater than 0, meaning the right subtree's left side is heavy. In this scenario, we need to perform a right-left rotation to balance the tree. Suppose we have a root node with a balance factor of -2, making it right-heavy. However, the right child has a balance factor of 1, indicating that its left subtree is heavier. To fix this imbalance, we first perform a right rotation on the right child, which shifts the left-heavy subtree into a more balanced form. Now the tree is in a right-right configuration. In the second step, we perform a left rotation on the original unbalanced node. This rotation adjusts the positions of the nodes, making the right-heavy node the new root and balancing the tree. Now we will use these 4 cases to code a method called rebalance. This method is triggered whenever an insertion or deletion causes the tree to become unbalanced. The purpose of this method is to identify which of the 4 cases has occurred and apply the appropriate rotations to restore balance to the AVL tree. This rebalance method takes the node that needs to be balanced as its input parameter. The first step is to calculate the balance factor of this node. If the balance factor is greater than 1, it means the tree is left-heavy. In this case, it further checks the balance factor of the left child. If the left child's balance factor is less than 0, indicating a left-right imbalance, it performs a left-right rotation on the node. Otherwise, it performs a right rotation for the left-left case. Similarly, if the balance factor of the node is less than -1, the tree is right-heavy. Here it checks the balance factor of the right child. If the right child's balance factor is greater than 0, indicating a right-left imbalance, it performs a right-left rotation. Otherwise, it performs a left rotation for the right-right case. If the balance factor is within the ideal range of -1 to 1, the node is already balanced, so the method simply returns the node without making any changes. This ensures that the AVL tree stays balanced after every operation, keeping the tree's height at log of n for efficient performance. In the AVL tree insertion algorithm, after completing the insertion logic, which is the same as in a regular binary search tree, we first update the height of the root node. This is necessary to ensure that the height property is accurate after the insertion. Next, we perform the rebalance operation on the root node. This step is crucial as it checks if the tree has become unbalanced due to the insertion and applies the appropriate rotations to restore balance. Similarly, the deletion operation follows a similar pattern. After performing the deletion logic, we update the height of the affected nodes and then call the rebalance method to ensure the tree remains balanced. For a complete implementation of these operations, you can find the code in the GitHub link provided in the description box below. Now let's see the AVL tree in action. First, we create an object called tree using the AVL tree class we implemented earlier. Let's start by inserting the value 10. Since this is the first node, it becomes the root, and the tree is balanced. Next, we insert 5. The tree is still balanced, as the balance factors of all nodes are within the acceptable range. Now, let's insert 2. The tree becomes unbalanced at this point because the left subtree is too heavy. The rebalance method gets triggered, and the appropriate rotations are performed to restore balance, in this case, a right rotation. Now, we insert 4. After this insertion, the tree remains balanced. But when we insert 3, the tree becomes unbalanced again. This time, the algorithm performs a right-left rotation to balance the tree. Lastly, let's delete the node with the value 10. After this deletion, the tree becomes unbalanced again, so the algorithm performs a right rotation to rebalance the tree. Through this series of insertions and deletions, we've seen how the AVL tree maintains its balanced structure, using rotations to ensure efficient performance. Let's understand how a red-black tree works. A red-black tree is a special type of self-balancing binary search tree in which each node can be either red or black. The leaf nodes, commonly referred to as nil nodes, are considered black by default. Now, a red-black tree has 5 key properties that are essential for maintaining its balance. First, we have already discussed that every node are either red or black. Second, the root node should always be black. Next, the nil nodes are always black. Furthermore, if a node is red, both of its children must be black. This means that a red node cannot have a red child, which prevents 2 adjacent red nodes from existing in the tree. Lastly, every path from a node to its descendant nil nodes must contain the same number of black nodes, ensuring that the tree remains balanced in depth. For example, let's consider this node with value 5. If we follow the path to the leftmost leaf node, we find there is only 1 black node in that path. Now, if we follow the path to any other leaf node in the tree, there will also be exactly 1 black node along the way. This demonstrates that the property of having the same number of black nodes in every path from a node to its leaf nodes holds true in this tree. This balance is what ensures the efficiency of operations in red-black trees. Now, keeping this property in mind, it's quite apparent that the height of the tree should be at most twice the black height. The black height is defined as the number of black nodes between the root and any leaf node, not including the leaf itself. Since there can be alternating red and black nodes in any path, the total height of the tree can be no more than twice the black height. Additionally, the number of nodes in a red-black tree should be at least 2 to the power black height minus 1. This is because the black height represents the minimum number of black nodes along any path from the root to a leaf. In the best-case scenario, where every level alternates between red and black nodes, the tree can have the fewest possible nodes while still maintaining its balance. This lower bound ensures that even in the most compact arrangement, the tree has a significant number of nodes relative to its height. By solving these 2 equations, we can determine the maximum height of a red-black tree. The height can be no greater than 2 times the logarithm, base 2 of n plus 1. This means that as the number of nodes increases, the height of the tree grows logarithmically, ensuring that the tree remains balanced and efficient for operations like search, insertion, and deletion. Now, let's take a look at the code for the node class. We will begin by defining the class node, which will accept the data and color of the node as input parameters. The color will be set to red by default. In the init method, we initialize the data attribute with the provided value and set the color attribute to red, unless specified otherwise. Additionally, we will define left, right, and parent attributes, all of which are initialized to none. This structure allows us to easily navigate and manage the relationships between nodes in the red-black tree. Next, we define the red-black tree class. Then inside the constructor, we initialize a sentinel node, referred to as nil, which represents the leaf nodes in the tree. This nil node is of type node and is set to be black. By using this sentinel node, we can simplify the logic for operations like insertion and deletion, as all leaf nodes will point to this single nil node, making it easier to manage tree boundaries. We also initialize the root of the tree to point to this nil node initially, indicating that the tree is empty at the time of creation. In this class, we will later define methods for various operations, including insertion and deletion of nodes. These operations will utilize the properties of the red-black tree to maintain balance and ensure efficient performance. Now let's focus on rotations. For the moment, we'll set aside the node colors and concentrate solely on the mechanics of the rotations themselves. Let's see the left rotation first. The goal of a left rotation is to move the right child of a node up, making the node itself the left child of its previous right child. We will begin by defining the rotate left method, which takes a node as input, representing the node on which the rotation will be performed. First, we identify the node X and set Y as the right child of X. Then, we shift Y's left subtree to become the new right subtree of X. If Y's left child exists and is not a nil node, we update its parent to X. After that, we link Y's parent to X's parent. If X was the root node, we update the tree's root to Y. If X was a left or right child of its parent, we update the parent's pointer to point to Y. Finally, we move X to become the left child of Y and set Y as the parent of X. That was the left rotation. Similarly, the right rotation works in the opposite direction. We'll rotate the root node to the right and assign the right subtree of its left child to the node's left. The process is straightforward and mirrors the steps of the left rotation, just in reverse. Visualizing these rotations becomes even simpler when there's no complex subtree in the way. Just rotate the node in the respective direction and update the necessary pointers. Now imagine the tree forms a zigzag shape, like a right-left structure. In this case, we first need to perform a right rotation on the right child node. After that, we perform a left rotation on the top node to balance the tree. Keep these concepts in mind, as they will play a crucial role in the insertion and deletion operations. Now, let's move on to the insertion operation. The key idea here is that we initially set the color of the node to be inserted as red, so it doesn't violate the property of having the same number of black nodes along every path. If the tree is empty, the new node becomes the root, and its color is changed to black. If the parent of the inserted node is black, no properties are violated, and the tree remains balanced. However, if the parent node is red, this creates a violation of the no2 adjacent red nodes property. In such cases, we need to perform recoloring and rotations to restore balance and fix the violation. Now, let's visualize the insertion process. First, let's insert the node with the value 10. Since it's the first node, it becomes the root and is colored black. Next, we insert 5. It is placed in its correct position, following the rules of a binary search tree, with 5 as the left child of 10. Since the parent, 10, is black, there are no issues. Then we insert 15 on the right side of 10. Again, the parent is black, so everything remains balanced. Now, let's insert 3. This time, the parent node, 5, is red, which creates a violation of the red-black tree property that no two red nodes can be adjacent. When this violation occurs, we need to check certain cases. The first case is when the parent node is the left child of its parent, and the parent sibling, also known as the uncle, is red. When this happens, we recolor both the parent and the uncle to black, and change the grandparent's color to red. After that, we move upwards and repeat this process to ensure the tree remains balanced. In this case, since the uncle node is red, we recolor both the parent and the uncle to black and the grandparent to red. However, if the grandparent is the root node, we recolor it to black to maintain the red-black tree properties. Now, let's insert the node with the value 2. This insertion again violates the red-red property. However, this time, the uncle node is a nil node, which is considered black by default. Therefore, in this scenario, the uncle is black. This case is a bit more complex and requires both recoloring and rotations to restore the balance of the tree. If the inserted node is the right child of its parent, we begin by performing a left rotation on the parent node. After the rotation, we recolor the parent to black and the grandparent to red. Finally, we carry out a right rotation on the grandparent to correct the imbalance and restore the properties of the red-black tree. In our case, the inserted node is the left child of the parent, so the condition for the right child is false. Therefore, we proceed to recolor the parent node to black and the grandparent to red. Next, we perform a right rotation on the grandparent to finally resolve the violations and restore balance to the tree. Now, let's insert the node with the value 4 into the tree. This insertion again violates the red-red property, and since the color of the uncle node is red, we only need to recolor the parent and uncle to black while changing the grandparent's color to red. After that, we will move upwards in the tree to check for any further violations. Now, let's insert the node with the value 20. In this case, the parent node is black, which means there are no violations of the red-black tree properties. Therefore, no further action is needed, and the tree remains balanced. Lastly, let's insert the node with the value 16. This insertion violates the red-red property. Here, the parent is the right child of the grandparent. When this occurs, the operations mirror those we discussed earlier. If the uncle node is red, we follow the same process as before. We color both the parent and the uncle black, while changing the grandparent's color to red, and then move upwards. If the uncle is black, and the inserted node is the left child, we perform a right rotation on the parent, recolor the parent to black, and the grandparent to red, and then execute a left rotation on the grandparent to restore the properties of the red-black tree. Finally, we ensure that the root node remains black. In this case, we first need to perform a right rotation on the parent node. After that, we recolor the parent to black and the grandparent to red. Finally, we perform a left rotation on the grandparent to restore balance to the tree. Now, let's look at the code for inserting elements into the red-black tree. First, we define the insert function, which takes the data to be inserted as an input parameter. In this function, we start by creating a new node with the given data and set its left and right children to the nil node. Next, we initialize two variables, parent, which will keep track of the parent of the new node, and current, which starts at the root. Next, we run a while loop until we reach a nil node, which helps us find the correct position for the new node in the tree. Inside the loop, we first update the parent to be the current node. Then, we check if the new node's data is less than the current node's data. If it is, we move to the left child. Otherwise, we move to the right child. Once the loop finishes, the new node's parent is set to the value of parent. If the parent is none, that means the tree was initially empty, so we set the new node as the root of the tree. Otherwise, we check if the new node's data is less than the parent's data. If it is, the new node becomes the left child of the parent. If not, it becomes the right child. Finally, we call the fixInsert method on the newly inserted node to correct any violations of the red-black tree properties. Next, let's see the code for the fixInsert method. This method is essentially the code implementation of the conditions we discussed earlier. We'll begin by defining the fixInsert function, which takes the newly inserted node as its input parameter. Inside this function, a while loop runs as long as the new node has a parent, and the parent's color is red, indicating a violation of the red-black tree properties. The first case we handle is when the parent of the node is the left child of the grandparent. In this case, we initialize the uncle node as the right child of the grandparent. If the uncle is also red, we recolor both the parent and uncle to black, and the grandparent to red. We then move up the tree by setting the grandparent as the new current node and continue the loop. However, if the uncle is black and the inserted node is a right child, we first make the new node, Z, the parent, and then perform a left rotation on the parent to adjust the shape of the tree. After this rotation, we recolor the parent to black, the grandparent to red, and finally perform a right rotation on the grandparent to correct the violation. If the parent is the right child of the grandparent, the process is symmetric. The uncle is now the left child of the grandparent. We apply similar logic. If the uncle is red, we recolor and move upward. If the uncle is black and the inserted node is a left child, we perform a right rotation, recolor, and then a left rotation on the grandparent. Lastly, after all the adjustments, we ensure that the root of the tree is always colored black, as required by the red-black tree properties. Now, before moving on to the delete operation, there are a few helper functions we need to review. The first one is the search function, which is used to find a specific element in the red-black tree. This function works recursively. It takes two parameters, the current node and the key we are searching for. If the current node is nil or its data matches the key, we return that node. If the key is smaller than the current node's data, we move to the left child. Otherwise, we move to the right child. This process repeats until we find the node or reach a nil node. The next helper function is minimum, which is used to find the node with the minimum value. This is especially useful when deleting a node that has two children. First, we define the function minimum, which takes the starting node as its input. The function works by traversing the tree, continuously moving left, as the smallest value in a binary search tree is always found at the leftmost node. The loop continues until it reaches a node whose left child is nil, indicating the minimum node. Finally, we return this node. The next helper function is transplant. This function is used during deletion to replace one subtree with another. It essentially moves the subtree rooted at node V into the position of node U. First, if node U is the root, we set the root of the tree to V. If U is the left child of its parent, we update the parent's left child to V. Otherwise, we update the right child. Finally, we set the parent of node V to be the parent of node U. This function is crucial for handling node replacement in the tree when deleting or rearranging nodes. Just like insertion, deletion also has cases, starting with the case when the node that replaces the deleted node is black. This is the node that will replace the node being finally removed. If the replacing node is the left child of its parent, we need to examine the color of its sibling. If the sibling node is red, the first step is to recolor the sibling black and the parent red. Then, a left rotation is performed on the parent to balance the tree. After this, we check again with a different configuration. If the sibling node is black and both of its children are also black, we can recolor the sibling red and move upwards, setting the parent node as the new focus of the fix-up. If the sibling is black, and the left child of the sibling is red while the right child is black, you first recolor the left child to black and the sibling to red, followed by a right rotation on the sibling. Now, if the right child of the sibling is red, the process is slightly different. In this case, we set the sibling's color to match its parent's color, then recolor the parent to black, and the right child to black as well, followed by a left rotation on the parent. Now, if the replacing node is the right child, the process is similar but mirrored. Instead of focusing on the left side, you look at the right side. If the sibling is red, recolor it to black and the parent to red, followed by a right rotation on the parent. If the sibling and both of its children are black, you simply recolor the sibling to red and move up the tree to the parent. If the sibling is black and its right child is red while the left child is black, you recolor the right child to black and the sibling to red, followed by a left rotation. Then, if the left child of the sibling is red, you set the sibling's color to its parent's color, make the parent black, and the left child to black as well, followed by a right rotation on the parent. Finally, ensure that the replacing node is always set to black. Now, let's see a few animated examples. In this tree, let's delete the node with the value 2. First, we'll delete the node as usual. The node that replaces it is the nil node, which is black. This triggers us to check for violations of the red-black tree properties, and we need to look at the sibling node and its color to decide what to do next. In this case, the sibling node is black, its left child is red, and its right child is a nil node which is black. This means we need to follow the rule where we recolor the left child to black, the sibling to red, and then perform a right rotation on the sibling node. Now, after the rotation, the configuration changes, and the right child of the sibling becomes red. In this situation, we'll change the sibling's color to match its parent's color, recolor the parent to black, and also recolor the right child of the sibling to black. Finally, we'll perform a left rotation on the parent node to complete the balancing of the red-black tree. Now let's delete the node with value 4. First, after finding it, we need to check for the minimum valued node in its right subtree, which is 5. We'll transplant the node with value 5 to the position of the node with value 4, effectively replacing it. Next, we establish the parent-child relationship between nodes 5 and 3. Since node 5 has now taken the place of node 4, we connect node 3 as the left child of node 5. Then, recolor node 5 to the color of node 4. At this point, node 4 is effectively removed from the tree, as no pointers lead to it. The only pointers that existed were from node 4 to its children, but these have now been replaced by node 5. Therefore, node 4 is completely disconnected from the tree. Now that the deletion has been completed, we need to fix the tree because the black height property is violated. The node that replaced the minimum valued node in the right subtree is a leaf node that is black. To restore the balance, we first check its sibling. The sibling is black, and both of its children are also black. In this case, we follow the red-black tree properties by recoloring the sibling red and moving up the tree. If you're unsure of how this works, refer back to the cases we've seen earlier during deletion fixes. As we move up the tree, we reach a red node. In this situation, we simply recolor this red node to black, which restores balance, and then we can terminate the process since no further adjustments are needed. Now, let's see the code for this. We'll start by defining the function delete that takes the target element as input, which is the value of the node we want to delete. First, we search for the node using the search function and store that into a variable z. If the node is nil, we stop the operation. We store the target node in a variable y, and we also keep the original color of the node in another variable. We then check if the left child of the target node is nil. If it is, we store the right child in a variable x, and then we transplant the target node with its right child. This process ensures that the target node is replaced by its right child, effectively removing the target node from the tree while maintaining the structure of the red-black tree. Similarly, if the right child of the target node is nil, we store the left child in the variable x, and then transplant the target node with its left child. Now, this x is the node that will replace the target node. This node is crucial because it will be the main focus during the rebalancing process and fixing any potential violations in the red-black tree's properties after the deletion. The cases for rebalancing the tree will be determined by this x. Otherwise, if the target node has two children, we will find the minimum node in the right subtree and store it in a variable y, while storing its color in another variable to track the original color. Then, we will store y's right child in a variable x. If the y's parent is the target node, then we will update the x's parent to y. Otherwise, we will transplant y with y's right child. After that, we will update y's right child to be z's right child, and set y's right child's parent to y. This step ensures that y takes the place of z and maintains the correct parent-child relationships in the tree structure. After that, we transplant z with y. We then set y's left child to z's left child and update y's left child's parent to y. Finally, we change y's color to match z's color. This ensures that the color of the node remains the same as the removed one. Finally, if the original color that we've stored in the variable is black, we perform the fix-delete operation by taking x as input. This function is crucial for fixing any red-black tree violations that may have occurred due to the deletion. It goes through the specific cases we've discussed earlier, such as handling sibling colors and performing rotations, to ensure that the red-black tree properties are restored and the tree remains balanced. Now, let's go through the fix-delete function. This function takes x, the node that replaced the deleted node, as input, and it ensures that the red-black tree properties are restored. The function runs inside a while loop that continues as long as x is not the root and x is black. The loop stops when the node reaches the root or the issue is resolved. First, if x is the left child of its parent, we get the sibling node, w, which is the right child of the parent. If the sibling is red, we recolor the sibling to black, the parent to red, and perform a left rotation on the parent. This fixes the imbalance caused by the deletion, and we reassign w to the new sibling after the rotation. This case handles the situation when the sibling is red, ensuring the tree stays balanced. Next, if the sibling w and both of its children are black, we recolor the sibling to red and move upwards in the tree, setting x to its parent. This step helps maintain the black height property, pushing the issue up the tree and allowing the fix to continue until the imbalance is resolved or the root is reached. If the sibling is black and its left child is red, while the right child is black, we recolor the left child to black and the sibling to red. Then we perform a right rotation on the sibling to set up for further adjustments. After the rotation, we reassign W to the updated sibling node and continue fixing the tree. Next, if the right child of the sibling is red, we recolor the sibling to match the parent's color, recolor the parent to black, and recolor the sibling's right child to black. Then, we perform a left rotation on the parent to restore balance and set X to the root, which terminates the process, as the tree is now balanced. The function also has symmetric cases when X is the right child of its parent. In these cases, the logic mirrors the left child's behavior, but we check and adjust the left sibling instead of the right sibling. Finally, after all adjustments, the function ensures that X is recolored to black, ensuring that the red-black tree properties are maintained. Now, grasping all these coding concepts, cases, and red-black tree operations might feel a bit tough at first. So, my advice is to head over to the GitHub link I've provided, where you'll find the Python code with detailed comments to guide you through each step. You can try inserting and deleting nodes in the tree and work through the logic yourself to get a clearer understanding of how everything functions. Hands-on practice will really help reinforce these concepts and make everything much easier to grasp. Let's dive into how heaps work, focusing specifically on binary heaps. A heap is structured as a complete binary tree, meaning that every level of the tree is fully filled except possibly the last, which fills from left to right. Now, heaps have a key property. In a max heap, each parent node is greater than or equal to its child nodes. Conversely, in a min heap, each parent node is less than or equal to its child nodes. In this video, we'll focus on max heaps, but keep in mind that min heaps function similarly with just the opposite ordering. Since a heap is a complete binary tree, it can be stored efficiently using an array instead of traditional nodes and pointers. This array representation makes heaps very efficient for operations like insertion and deletion. First, we store the root node at the 0th index of the array. Then, we add its left child, followed by its right child, and continue in this manner, level by level, from left to right. This layout allows us to access any parent or child node using simple index calculations. Now let's look at the formulas for finding the parent and children of any element, given its index in the array. For example, consider an element with the value 30 at index 2. To find its left child, we plug I equals 2 into the left child formula, which gives us index 5. So index 5 is the left child of the element at index 2. Similarly, using the right child formula with I equals 2, we can find the right child's index. To locate the parent of the current node, we use the parent formula with IC equals 2 and take the floor of the result to determine its parent index. This simple indexing allows efficient traversal up and down the heap. Now, let's look at the Python code to implement everything we've learned so far. We'll start by defining a class called maxHeap. Inside the constructor, we'll initialize an empty array called heap to store our elements. Next, we'll add methods to find the left and right children, as well as the parent of any element based on its index. One important thing to keep in mind is that the height of a complete binary tree is logarithmic. Now, let's take a look at how insertion works in a max heap. Suppose we want to insert the value 43 into our max heap. To do this, we first append 43 to the end of the array, which is equivalent to placing it in the next available leaf node in the complete binary tree structure. Now the newly inserted element might be violating the max heap property. To fix this, we check if this element is greater than its parent. If it is, we swap them to restore the heap structure, effectively bubbling up the element. We continue this process, comparing and swapping with each successive parent until the heap property is restored, or the element reaches the root. Keep in mind, the tree structure we visualize is just to help us understand the relationships between elements. In reality, all heap operations happen directly within the array itself. Now, let's look at the Python code for the insertion operation. We'll start by defining an insert method that takes the element we want to insert as an input parameter. First, we append this element to the end of the heap array. Then, we perform the heapify up operation on this element to ensure it fits into the max heap structure. The heapify up function takes the index of the newly inserted element as its input parameter. Inside this function, we use a while loop that runs as long as the current element is not the root, and the parent element is smaller than the child. Within the loop, we swap the parent and child elements to maintain the max heap property. After each swap, we update the index to the parent's index, effectively moving the element up the heap until it's in the correct position or reaches the root. Now, deleting an element in a max heap typically means removing the root node, which has the maximum value in this structure. To do this, we start by replacing the value of the root node with the value of the last element in the heap, in this case 13. Then, we remove the last element, which effectively removes the original root. However, the new root might violate the max heap property, so we need to restore the structure. To do this, we perform heapify down operation, moving the root element down the tree until it's in the correct position to maintain the max heap order. We start the heapify down process by comparing the current element with both of its children. If either child is larger than the current element, we swap it with the child that has the larger value. In this case, we swap with the left child with value 43. Next, we compare again and swap with the right child, which has the value 40. Finally, we compare the current element with its only remaining child. Since this child has a value less than the current element, no swapping is needed, and the process terminates. At this point, the max heap property is restored, and the heap structure is complete. The maximum number of swaps we might need to perform is equal to the height of the tree, so the time complexity for both insertion and deletion operations is big O of log n. Additionally, since these operations only rearrange elements within the existing array, they don't require any extra memory. This means the space complexity remains constant. Next, let's look at the code. First, we will start by defining the extract max function. We start by checking if the heap is empty. If it is, we simply return, as there's nothing to extract. Otherwise, we store the root element in a variable called maximum. Then, we replace the root element with the last element in the array and remove the last element from the heap. Finally, we call heapify down to restore the max heap property, and once the structure is balanced, we return the maximum value. Next, let's go over the details of the heapify down function. This function takes the index of the element that needs adjustment. We start by storing the size of the array in a variable called size and initializing another variable, largest, with the current index, assuming this element is the largest for now. We then enter a loop where we calculate the indices of the left and right children of the current element and store them in left and right variables. We then check if the left child exists and if its value is greater than the current element's value. If it is, we update largest to the left child's index. We then do a similar check for the right child. If it exists and has a larger value, we update largest to the right child's index. If, after these checks, largest is not equal to the current index, it means we've found a larger child, so we swap the current element with this larger child. We then update index to largest and continue the loop to further adjust the heap. However, if largest is still equal to the current index, it means the element is in the correct position, so we can break out of the loop. This completes the heapify down process. The next operation we'll look at is building a heap from a given array. Let's say we have an array and its corresponding tree structure, which initially does not satisfy the max heap property. Our goal is to transform this array into a max heap. To build a max heap, we start from the lowest non-leaf node and perform the heapify down operation on each node, working our way up to the root. The reason we begin from the lowest non-leaf node is that, in a complete binary tree, about half of the nodes are leaf nodes, and they don't need to be heapified. The lowest non-leaf node is found at index n upon 2 minus 1, where n is the total number of elements in the array. This is because, in a complete binary tree, all nodes from this index onward are leaf nodes, so the last non-leaf node will be one position before them. So, we'll begin at the last non-leaf node and iteratively perform the heapify down operation on each of these nodes, working our way up to the root. By applying heapify down from the bottom up, we ensure that every subtree satisfies the max heap property before moving up a level. Now, let's examine the complexity of building a heap from an array. At first glance, it might seem like, since there are about n/2 nodes on which we perform the heapify down operation, each potentially taking up to log n time, the time complexity should be big O of n log n. However, this is not a tight bound. To understand why, let's consider how heapify down behaves at different levels in the heap. First, we don't perform any heapify down operations on the leaf nodes, so no swaps are needed at that level. Moving one level up, we find that each node requires, on average, just one swap to maintain the heap property. As we go up another level, nodes may need around 2 swaps each, but the number of nodes at this level is reduced by half. At the level above that, each node may require 3 swaps on average, and again, the number of nodes continues to decrease. This pattern continues, with nodes at higher levels requiring more swaps, but fewer nodes existing at each of these levels. This pattern can be represented mathematically by summing the work done at each level. As we move up the levels, the work done per node increases, but the number of nodes decreases proportionally. When we solve this summation, it converges to big O of n, showing that the total work required to build the heap is indeed linear in time complexity. Now, let's look at the code for building a heap from an array. We'll start by creating a function called buildHeap, which takes an array as its input. Inside this function, we'll set our heap to be this input array. Then, we'll run a loop starting from the last non-leaf node and move all the way up to the root node in reverse order. For each node in this range, we'll perform the heapify down operation. Now, let's build a priority queue using a heap. A priority queue is a special type of queue where each element has an associated priority. When we insert elements, they are arranged based on this priority, and when we pop elements, the one with the highest priority is removed first. First, we'll create an object using the max heap class we've already built. This heap will serve as the core structure of our priority queue. We'll insert elements along with their priorities, treating the priority as the key for organizing the heap. When we remove elements, they'll be popped in order of their priority, with the highest priority element being removed first. This way, our max heap provides the ideal mechanism for efficiently managing and accessing the highest priority items in the queue. Check out the description box below for a link to the GitHub repository, where you'll find all the code we've covered in this video.
A hash table is a data structure that stores elements as key value pairs, allowing you to use the key to efficiently retrieve information about its corresponding value. Here in this example, we have some keys representing names, Alice, Bob, and Oscar, and their corresponding university IDs as their values. If we want to retrieve the ID of, say, Bob, we can use Bob as the key to efficiently access his ID. In practice, we use something called a hash function, which takes the key as input and returns the location where the corresponding value is stored. In practice, this is implemented using arrays. Let's consider an array of size 8, with indices ranging from 0 to 7. We'll use a hash function that takes the key and performs a modulo operation with the size of the array, which in this case is 8. For simplicity, let's assume the key is a positive integer. Now, let's insert a key value pair with the key 12 and the value Alice. we'll pass the key 12 into our hash function, and the output of the hash function will determine the index of the array where the value Alice will be stored. Here, the output is 4, which means we need to store this key value pair at index 4 of the array. Next, let's insert the value Bob with the key 10. Passing the key 10 into the hash function gives an output of 2. This means we need to store the key value pair at index 2 of the array. Next, let's insert the value Oscar with the key 8. Passing the key 8 into the hash function gives an output of 0. This means we need to store this key value pair at index 0 of the array. Next, let's insert the value Vivek with the key 2. This one is interesting because when we pass the key 2 through the hash function, it gives the index 2. However, index 2 is already occupied, so we can't store the value there. This, ladies and gentlemen, is known as a collision. A collision occurs when the index provided by the hash function is already occupied. There are multiple ways to handle collisions. First, let's understand how chaining helps deal with collisions. Let's use the same 8-sized array as an example. Suppose we insert the value A with the key 4. If you perform the modulo 8 operation, you get the index 4. So we need to store this value at index 4. However, instead of directly storing it at index 4, we use a linked list to store the value at that index. Now, if we store another element with the key 12, the hash output would again be 4, resulting in a collision. To handle this, we add the new element to the end of the linked list at index 4. If you're unfamiliar with how a linked list works, you might want to check out our video on linked lists. The link is in the description box below. Other elements will be inserted similarly, creating a new linked list at each index. When a collision occurs, the element is appended to the end of the linked list at that index. Now, deleting an element works in a similar fashion. Let's delete the element with the key 12. First, the index is calculated by passing the key through the hash function. Then, the key is searched within the linked list at that index. Once the element is found, it is deleted, and the next pointer of the previous node is updated to point to the next node, effectively removing the element from the linked list. Now, insertion and deletion in a hash table are generally constant time operations on average if the hash function is effective. However, if too many keys collide, the operations can degrade to linear time in the worst case. Now let's look at another collision handling technique called open addressing. In this method, we'll first explore a strategy known as linear probing. In linear probing, when a collision occurs, we try to find the next available slot to insert the element. For example, if index 4 is already filled, we move to the next index, 5. Since index 5 is empty, we insert the element there. Next, if a key is hashed to index 4 again, we check the next slot. In this case, index 5 is already filled, so we continue searching until we find the next available slot. Here, index 6 is empty, so we insert the element there. The formula for linear probing is hash of the key plus the loop variable I, and then take modulo with the size of the array. This ensures that if I goes out of range, it wraps around to the earlier positions in the array. Now, the disadvantage of linear probing is that it can form clusters of elements near each other, which makes the operations inefficient. Let's move on to another technique within open addressing called quadratic probing. In quadratic probing, instead of searching for an empty slot in a straight line, we search in a quadratic pattern. The formula is similar to the one we used earlier, but here we use I squared instead of just I. Here we have an element with the key 1. If we take the modulo 8 of it, we get 1. So let's insert it at the first index. And the next element with the key 2 will go to index 2. Now let's insert the element with the key 9. The hash output would be 1, but index 1 is already occupied. So we apply the formula to find the next available slot. Using the formula, we take the hash value 1 and the variable I equals 1. Substituting into the formula gives the result 2. But index 2 is also occupied. In the next iteration, we increase I to 2 and calculate again. This time, the formula gives the result 5. Index 5 is empty, so we insert the element at index 5. This technique works well for larger arrays. However, if you observe the pattern, you'll notice that in the next iteration, it can go back to an already visited index, like index 2, and get stuck in a cycle. Double hashing can solve the issue of cycles, so let's look at how this technique works next. The idea in double hashing is that if a collision occurs, instead of probing in a linear or quadratic sequence, we use a second hash function to determine the step size for the next probe. This ensures a more scattered and independent probing sequence, reducing clustering and avoiding cycles. Here, m represents the array size, which is 8 in our example. A common second hash function used in double hashing is tp minus key modulo p. Here, p is a prime number smaller than the size of the array. In our example, we'll take p equals 5. This second hash function ensures the step size is independent, helping to avoid clustering and cycles. Let's insert an element with the key 2. The hash output is 2, and since index 2 is empty, we'll insert the element there. Next, let's insert the element with the key 10. The hash output is 2, so it should be placed at index 2. But since index 2 is already occupied, we'll use double hashing. First, we calculate the second hash function using 10 as the key. The output is 5. Now we plug this into the formula, where the first hash value is 2, I equals 1, and the second hash output is 5. This gives us an output of 7. So we will check if index 7 is empty. It is empty, so we will insert the element there. Next, in one last example, let's insert a value with the key 18. The hash output is 2, so it should go to index 2. But since index 2 is already occupied, we calculate the second hash function using the key 18. The output is 2. Now, using the formula with the first hash value 2, I equals 1, and the second hash output 2, we get 4. We check if index 4 is empty. It is, so we insert the value there. That's how double hashing works. The time complexity of all operations in a hash table is constant time on average. However, in the worst case, it can degrade to linear time if there are too many collisions. But this scenario is rare with a good hash function and a well-designed table. Check out the GitHub link in the description for a simple Python implementation of this.
Let's talk about graphs. A graph is a data structure made up of nodes, also known as vertices, and edges, which are the connections between those nodes. Think of it like a network, where each node represents an object or entity, and each edge represents the relationship or connection between them. The graph you are seeing is known as an undirected graph, where the connections between nodes have no direction. This means that if there is an edge between two nodes, you can move between them in both directions. A directed graph, on the other hand, is one where the edges have a direction. This means that the connections between nodes only allow movement in one specific direction, from one node to another. A graph can either be weighted or unweighted. The graph on the screen is an example of an unweighted graph, where there is no cost associated with moving from one node to another. A weighted graph, however, has a specific weight or cost assigned to each edge, representing the cost of moving between nodes. In this example, the weight of the edge between node A and node B is 3, meaning it will take 3 units of cost or effort to move from A to B. Another important concept is the degree of a node. The degree of a node refers to the number of edges connected to it. In an undirected graph, this is straightforward. The degree of a node is simply the number of edges connected to it. For example, the degree of this node G is 3 because it has 3 edges connected to it. In a directed graph, however, the degree is split into 2 parts, the in degree and the out degree. The in degree represents the number of edges coming into the node, while the out degree represents the number of edges going out from the node. Now, there are other types of graphs, like parallel graphs, where multiple edges can exist between 2 nodes, or graphs with self-loops, where an edge is directed back to the same node. However, we won't be covering those in this video. Next is the concept of connected graphs. A graph is called connected when every node is reachable from every other node. In a connected graph, there are no isolated nodes, and all nodes are part of a single connected component. In this example, the graph is not connected. To make it connected, we need to add edges between certain nodes so that every node can reach every other node. Let's now explore how many minimum edges are required to keep a graph connected in the undirected case. We'll start with one node. This is considered connected on its own. If we add a second node, we we need to connect them with an edge. Now, if we add a third node, we need another edge, and so on. You can see the pattern. The minimum number of edges needed to keep a graph connected is always one less than the number of nodes. So, for a graph with n nodes, the minimum number of edges required is n-1. Now, what about the maximum number of edges? This happens when every node is connected to every other node. In the case of undirected graphs, the maximum number of edges is equal to the number of ways to choose two nodes out of n nodes, which is given by the formula n times n-1 divided by 2. What about the minimum number of edges in a directed graph to keep it connected? This is a bit tricky because the edges are unidirectional. So, when we connect the nodes like before, we can only reach nodes in one direction. In this case, the graph is considered weakly connected, meaning the nodes are connected, but not every node is reachable from every other node. To make the graph strongly connected, we need to add a directed edge from the last node back to the start node, ensuring that every node is reachable. This forms a simple directed cycle, where each node has both an incoming and outgoing edge, ensuring strong connectivity. So, the minimum number of edges required in this case is n. Now, the maximum number of edges in this case means every node is connected to every other node. This would be twice the number of edges compared to the undirected case, because now there are two edges for each pair of nodes, one in each direction. Now, let's see how a graph is represented. First, let's look at the adjacency matrix. In an adjacency matrix, we use a two-dimensional grid where each cell represents whether there is an edge between two nodes. If there is an edge, we put a 1 in the corresponding cell, and if not, we put a 0. Each node has one row and one column in the matrix. Here, the rows represent the starting nodes, and the columns represent the destination nodes. For example, this cell represents whether there is an edge from node A to itself, which would be a self-loop. Since there is no self-loop here, we will mark this cell as 0. We'll do the same for all the diagonal elements, as they represent self-loops. Now, this cell represents whether there is an edge from node A to node B. Since there is an edge here, we will mark it with a 1. We will similarly fill all the cells based on the presence or absence of edges between nodes. Notice one thing carefully. In an undirected graph, going from one node to another is the same as returning from that node, so the matrix will be symmetrical. However, in a directed graph, an edge can only go in one direction, so we will fill the matrix accordingly, without symmetry. Just like before, all the diagonal elements will be 0 because there are no self-loops. However, now, while filling the cells, we will check if there is a directed edge from the row node to the column node. If there is, we will mark it with a 1. Otherwise, it stays 0. Notice how the matrix is not symmetrical along the diagonal in a directed graph. This is because the edges have a specific direction, unlike in undirected graphs where the matrix is symmetrical. If the graph contains weights, we use a different symbol to represent the absence of an edge. In our case, let's use asterisk. Now, to represent the edges, we simply replace the ones with the corresponding weights of those edges. Now, this matrix is of n by n dimensions, where n is the number of nodes in the graph. So the space complexity of this representation is big O of n squared, which can be a bit expensive in terms of memory usage. Now, to find all the neighboring nodes of a given node, let's say node B, we need to traverse that row of the matrix. This operation takes linear time, meaning the time complexity will be big O of n. Now, adding an edge is a constant time operation since it only requires updating the target cell in the matrix. This means the time complexity for adding an edge is big O of 1. Similarly, removing an edge is also a constant time operation, as it only requires updating the corresponding cell in the matrix. Now, removing a vertex is a bit trickier. Let's say we want to remove vertex B. To represent this in the matrix, we have to remove both the row and column corresponding to that vertex. To do this, we need to create a new matrix with one less dimension and copy all the elements except for the ones related to the vertex we are deleting. This new matrix then becomes the updated adjacency matrix for the graph. Removing nodes takes big O of n squared time complexity because we need to copy the elements from one matrix to another, which involves updating both rows and columns. Now, adding a vertex is exactly the opposite of removing one. We create a new matrix with one extra dimension, copy all the elements from the old matrix to the new one, and add the new row and column for the vertex. This operation also takes O of n squared time complexity because we need to copy all the elements from the original matrix into the new one. This operation can be optimized if we start with a larger matrix initially, but that would waste a lot of space since unused rows and columns would remain empty. Another way to represent a graph is by using an adjacency list. In an adjacency list, each node is associated with a list that contains all the nodes it's directly connected to. For example, the node A here is only connected to node B, so we will only store B in the adjacency list of A. This way, we only store the nodes that A is directly connected to, making the representation more efficient. Similarly, the adjacency list for the other nodes will be created, with each node only storing its direct connections. In the case of a directed graph, each adjacency list will only store the edges that are going out from the node. This means we only keep track of the nodes that can be reached directly from the current node. Now, if the graph is weighted, we simply pair each edge in the adjacency list with its corresponding weight. This way, each connection not only shows the destination node, but also the cost or weight associated with that edge. The space complexity for an adjacency list is big O of n plus e, because for each node, we only store its direct connections. We need space for each node, which is big O of n, and for each edge, we store it in the list of the node it's connected to. In an undirected graph, each edge is stored twice, while in a directed graph, each edge is stored once. This means the total space required depends on both the number of nodes and the actual number of edges. However, when the graph is dense, the number of edges tends to approach the square of the number of nodes. In that case, the space complexity of the adjacency list also becomes close to big O of n squared. Now, adding an edge is a constant time operation because we only need to append that edge to the adjacency list of the node. If it's a directed graph, like this one, we append it once to the starting node's list. In the case of an undirected graph, we need to append the edge to both connected nodes' lists. Now, removing an edge requires searching for that particular edge in the adjacency list of the node. The number of edges present in the list will be equal to the out degree of that node, which means the time complexity for removing an edge is proportional to the out degree of the node. In the case of an undirected graph, removing an edge means we need to search for the target edge in the adjacency lists of both connected nodes. In this case, we need to search the list of both nodes B and D. So, the time complexity in this case would be proportional to the sum of the degrees of both nodes involved in the edge. Now, removing a node is a bit tricky. Let's say we remove node B. The first step is to delete the adjacency list of this node, which is a constant time operation. Then, we also need to remove all references to this node from the adjacency lists of all other connected nodes. In the case of an undirected graph, these references can be easily found in the adjacency list of the deleted node. However, in a directed graph, we may need to search all adjacency lists to find any references to the node, which can potentially take big O of n plus e time in the worst case. Now, adding a node is a constant time operation because it only involves creating an empty adjacency list for the new node without affecting the other nodes or edges. So, that was pretty much the introduction to the graph data structure. In the next few videos, we will dive into traversal algorithms like breadth-first search and depth-first search, minimum spanning tree algorithms like Prim's and Kruskal's, and shortest path algorithms like Dijkstra's, along with others. Let's see how a depth-first search, or DFS, algorithm works in a graph. Here we have this graph, and the corresponding adjacency list showing how each node connects to others. Our goal is to explore it using DFS. We'll start with the recursive approach first. On the right, we have this recursion stack, which helps us keep track of where we are in the search as we go deeper into each path. Let's begin DFS from node A and see how we move from one node to the next. First, we'll print node A to mark the start of our DFS journey. Now we need to move to one of its neighbors. Since A has 2 neighbors, which one should we visit first? The order depends on how the nodes are stored in the adjacency list. In our case, node B appears before node C, so we'll follow that order and proceed to node B. Now, node B also has 2 neighbors, but since we've already visited A, we'll move on to the next neighbor, which is G. Node G also has 2 unvisited neighbors. According to the order in the adjacency list, node F comes first, so we'll proceed to F from here. Now looking at node F, we see that node C comes before node E in its adjacency list. So, our next move will be to visit node C. Now that all the neighbors of node C have been visited, the algorithm will backtrack from here. We'll return to node F and move to its other neighbor, which is node E. From node E, the algorithm will move to its only unvisited neighbor, which is node D. Now, since node D has no unvisited neighbors, the algorithm will begin backtracking from here, checking for any unvisited nodes as it retraces its steps. Now, let's take a look at the code for this recursive version of DFS. First, we'll store the graph as an adjacency list, using a dictionary where each node points to a list of its neighbors. Next, we'll define the DFS function, which takes 3 input parameters: the graph, the starting vertex, and a set called visited to keep track of nodes we've already visited. In this function, we add the current vertex to the visited set and print it to show our progress. Then, for each neighbor of the current vertex, we check if it's already visited. If it's unvisited, we recursively call DFS on that neighbor, continuing our deep exploration. The time complexity of this DFS algorithm is big O of n plus e, where n is the number of nodes and e is the number of edges. This complexity arises because the algorithm visits each node once and, for each node, checks all its connected edges. Thus, we account for both nodes and edges in the overall complexity. The space complexity of this DFS algorithm is big O of n, where n is the number of nodes. This is due to the recursive call stack, which, in the worst case, can go as deep as the number of nodes if the graph is skewed like a single path. Additionally, the visited set also requires O of n space to store each node once as it's visited. Now, let's explore the iterative version of the DFS algorithm. First, we initialize an empty set to keep track of nodes we've already explored, and an explicit stack to manage the traversal. Initially, this stack will contain just the starting node, A. Next, we'll pop the top element from the stack and check if it's already visited by looking it up in the visited set. If it hasn't been visited, we'll add it to the set, print it, and mark it in orange to visually track the traversal. Now, this node has 2 neighbors, so we'll check its adjacency list. Here, the neighbors appear in the order B and C. However, we'll push them onto the stack in reverse order, first C, then B. This is because the stack follows a last in first out order. By pushing node B last, it will be the first to be processed, maintaining the correct traversal sequence. Next, node B is popped from the stack. Since it's not in the visited set, we'll add it, print it, and mark it in orange to show our traversal. Now, we'll look at B's neighbors. A is already visited, so we'll skip it and push G onto the stack. Now we'll pop G from the stack, add it to the visited set, print it, and mark it in orange. Now, G has 2 unvisited neighbors. We'll push them onto the stack in reverse order, as usual, to maintain the correct traversal sequence. Now, we'll pop node F from the stack, add it to the visited set, print it, and mark it in orange. Next, node F has 2 unvisited neighbors, C and E. As before, we'll push them onto the stack in reverse order, so E goes first, followed by C. Now, we'll pop node C from the stack, as it is not in the visited set. We will add it to the visited set, print it, and mark it in orange. Now, since node C has no unvisited neighbors, we'll pop the next element from the stack, which is node E. Since E isn't in the visited set, we'll add it there, print it, and mark it in orange. Now node E has an unvisited neighbor, D, so we'll push D onto the stack. Now, as usual, we'll pop the top element from the stack, which is D. Since D isn't in the visited set, we'll add it, print it, and mark it in orange. Now, node D has no unvisited neighbors, so we'll pop the stack. The popped element is C, but since C has already been visited, we'll skip it and pop the stack again. Once again, we get C, so we skip it. Now that the stack is empty, the algorithm stops here. Now, let's take a look at the code for this iterative DFS method. First, we define the function, which takes two input parameters, the graph and the start node. Inside, we initialize an empty set to track explored nodes and a stack that begins with the starting node. Then, we enter a while loop that will continue running as long as there are elements in the stack. Inside the loop, we pop the top element from the stack, which gives us the current node to process. If this node hasn't been visited yet, we add it to the visited set, print it, and mark it for traversal. After that, we look at its neighbors in the adjacency list. To maintain the correct order, we push each unvisited neighbor onto the stack in reverse order. This ensures we process them in the desired sequence when popped. For all the code used in this video, be sure to check out the GitHub link provided in the description box. The time complexity for this iterative approach remains big O of n plus e, where n is the number of nodes and e is the number of edges. The space requirement is big O of n, as we use a visited set and an explicit stack to store nodes. Let's see how BFS, or breadth first search, operates on a graph. Here, we have a graph along with its corresponding adjacency list, which represents its connections. Unlike depth first search, which explores as deep as possible along each branch, breadth first search doesn't dive deep right away. Instead, it traverses the graph layer by layer, exploring all neighbors at the current level before moving to the next. Now, let's see how the algorithm works in this example. First, we initialize a queue with the starting node, in our case node A, as the initial value. We also create an empty set to keep track of the nodes we visited. Understanding the queue data structure is essential to grasp how BFS operates. If you're not familiar with queues, we have a detailed animated video on the topic, linked in the description box below. Now, a while loop will run as long as the queue is not empty. First, we remove the leftmost element from the queue and check if it has already been visited. If not, we add it to the visited set, print its value, and mark it in orange to visually indicate that the node has been visited. Next, we append any unvisited neighbors of the current node to the queue. In this case, both neighbors of the node are unvisited, so we add both to the queue. But what about the order? For that, we refer to the adjacency list of the graph, which contains the sequence in which the neighbors are stored. In this case, node B appears before node C in the adjacency list, so we append them to the queue in that order, first B, then C. In the next iteration, we again pop the leftmost element from the queue and check if it has been visited. Since it hasn't, we add it to the visited set, print its value, and color it orange to indicate it's been visited. Next, we append its unvisited neighbors to the queue. Here, node G is the only unvisited neighbor, so we add G to the queue. In the next iteration, we pop element C from the queue, add it to the visited set, print it, and then insert its unvisited neighbor into the queue. Here, two of C's neighbors are unvisited, with node G appearing before node F in the adjacency list. So we'll insert node G first, followed by node F. Next, we pop element G from the queue, add it to the visited set, print it, and then insert its unvisited neighbor into the queue. Next, we pop the element from the queue again. This time, the element is already visited, so we'll skip it and move on to pop the next element. We'll check if the element is visited. If it's not, we'll add it to the visited set, print it, and insert its unvisited neighbors into the queue. Next, the popped element is already present in the visited set, so we will skip it and move to the next one. This time, the popped element is not in the visited set, so we will add it, print its value, and insert its unvisited neighbors into the queue. Next, the popped element is D, which is not in the visited set, so we will add it, print its value, and insert its unvisited neighbors into the queue. Since there are no unvisited neighbors left for this node, we'll skip adding any new elements. Now the queue is empty, meaning the traversal is complete, so the algorithm will stop. Now, let's look at the code. First, this is how to store the graph in an adjacency list using Python dictionaries and lists. Next, we'll start by importing the decay structure from Python's collections module to use as our queue. Then, we define the BFFs function, which takes the graph and the starting node as input parameters. Next, we define a set to track all visited nodes during the traversal, along with a queue that starts with the initial node. We also create an empty list to store the traversed elements in the order they are visited. Next, a while loop runs as long as the queue isn't empty. Inside the loop, we first pop the element from the front of the queue and check if this node has been visited. If it hasn't, we add it to both the visited set and the traversal list. Then, we check each neighbor of the current node. If a neighbor is unvisited, we add it to the queue and continue the process. After the loop completes, we return the traversal list, which contains the nodes in the order they were visited. Now, the time complexity of this algorithm is big O of n plus e, where n represents the number of vertices, or nodes, and e represents the number of edges in the graph. This is because each node and each edge is processed once during the traversal. The space complexity of BFS is big O of n, where n is the number of nodes in the graph. This complexity arises from the maximum size of the queue, which, in the worst case, can hold all nodes in the graph, as well as the visited set that stores all visited nodes.
A minimum spanning tree is a subset of a graph that connects all the vertices with the minimum possible total edge weight. It ensures the graph remains connected and contains no cycles. Now, let's find the minimum spanning tree for this example graph using Prim's algorithm. We'll start by selecting a vertex and progressively add edges with the smallest weights while ensuring the graph remains connected and cycle-free. Let's begin with node A. From here, we examine all the edges connected to A and select the one with the smallest weight to include in our tree. We can use a priority queue to store the edges, allowing us to quickly retrieve the edge with the minimum weight. Here, the edge AB has the minimum weight of 2, so we add this edge to our spanning tree. Next, we examine all the edges connected to node B to continue building the tree. Now, among all the highlighted edges, we select the one with the minimum cost. In this case, it's the edge BD with a weight of 2, so we add this edge to our spanning tree. Next, we examine all the edges connected to node D, and once again select the edge with the minimum weight. Here, we choose the edge DC with a weight of 1 and add it to our spanning tree. Now, we again select the edge with the minimum weight. Here, it's the edge AF with a weight of 3, so we add it to our spanning tree. With this addition, all the nodes are now connected, and the algorithm stops. Now, we are left with the minimum spanning tree. Here's an interesting observation. In any minimum spanning tree, there will always be exactly v-1 edges, where v is the number of vertices in the graph. This is because if there were fewer edges, the graph would be disconnected, and if there were more, it would form cycles, which is not allowed in a tree. Let's look at the Python code for this algorithm. First, we import the heap queue module, which helps us implement the priority queue. Then we define the function, which takes the graph and the starting node as input parameters. Then we initialize some variables to work with. First, a priority queue to store edges, a set named visited to store the visited nodes, MST edges to store the edges that will be part of the minimum spanning tree, and the total cost variable to store the total cost of the minimum spanning tree. Then we add the starting node to the visited set and push its neighboring edges along with their weights onto the priority queue. This assumes the graph is stored in an adjacency list. Then, as long as the priority queue is not empty, we pop the element with the lowest weight and check if the node is already in the visited set. If not, we add it to the visited set, add the edge to the minimum spanning tree, update the total cost, and push all the edges connected to the current node onto the priority queue. And finally, we return the edges and the total cost of the minimum spanning tree. Check out the link in the description for the GitHub link to the full code. Now, iterating over all the edges is of the order big O of E, and every edge can be pushed into the priority queue almost once. Each push operation takes logarithmic time, so the total time complexity will be big O of E log V. The graph takes big O of V plus E space as it is stored in an adjacency list. The visited set takes big O of V space because it stores at most V vertices. The priority queue takes big O of E space as it may hold up to E edges during the execution. The edge list for the minimum spanning tree takes big O of V space. Hence, the total space complexity is big O of V plus E. Let's understand how Kruskal's algorithm finds the minimum spanning tree of a graph. A minimum spanning tree is a subset of a graph that connects all vertices with the minimum total edge weight and no cycles. The idea is to first sort all the edges in ascending order of their weights, and then add them to the spanning tree one by one in that order. The first edge has a weight of 1, so let's add it to our spanning tree. Next, we consider the edges with a weight of 2. Since there are 2 such edges, we can choose either one. The selection depends on how the graph is stored. The next edge has a weight of 2, but it forms a cycle, so we skip it and do not add it to our spanning tree. The next edge has a weight of 3, so we add it as usual. Then comes the edge with a weight of 4, but since it forms a cycle, we skip it. Next is the edge with a weight of 5, which we add as usual. Now, as you can see, all the nodes are connected, so the algorithm stops. Observe carefully. The minimum spanning tree always contains edges equal to 1 less than the number of nodes in the graph. Now, let's understand how cycle detection works. Here, we have some disconnected graphs. Each graph will have its own set. If 2 elements belong to different sets, it means they are not connected. However, if they belong to the same set, it means they are connected. If we connect an edge between nodes X and P, we need to perform a union operation on the sets to which they belong. Similarly, if we connect an edge between nodes Q and M, the same union operation will be performed on the sets containing those nodes. Now let's connect P and N. It is forming a cycle, but how can we know? To check, look into the sets. If both P and N are in the same set, it means they form a cycle. So that's how cycle detection works. If both nodes are in the same set, it means there is a cycle. Otherwise, there is no cycle. Now, let's dive deeper into how disjoint sets work. Here, we have a table with all the nodes, along with a parent table where each node is considered its own parent, and a rank table that contains the rank of each element. The significance of these will become clear in a moment. For now, just remember that initially, each node is its own parent. When this happens, we consider the element as its root, meaning each element is its own root. At this stage, every element is in its own separate set. Now, we have 2 main operations on disjoint sets. The first is the find operation, which determines the root of an element. This root can then be compared to the root of another element, and if they match, it means both elements belong to the same set. The second operation is the union operation, which is used to merge 2 sets. For example, if we perform the find operation on the elements A and C and check their parents, it turns out they are their own parents. This means they are the roots. Since the roots for both are different, it indicates that A and C belong to different sets. Now, let's perform a union operation on A and B. If we check their parents, it turns out they are both their own parents and roots. Looking at their ranks, we see they are the same. In this case, we can choose one to be the parent of the other. Let's make A the parent of B. After this, we increment the rank of A. We could have made B the parent of A and incremented B's rank instead. It doesn't matter in this case. The significance of the rank is that if one element has a higher rank, it should be made the parent of the other. If their ranks are equal, we can choose either one as the parent. Now let's perform a union operation on A and C. Here, both A and C are their own parents, meaning they are the roots. Since the rank of A is higher than the rank of C, we will make A the parent of C. Similarly, in the next example, we perform a union operation on D and G. In the last example, let's perform a union operation on A and D. In this case, both elements have the same rank, so we will make A the parent of D. Now let's perform the find operation on E. We check its parent, which is also E. This means E is the root, and we found it in constant time. Now let's find the root of the element G. First, we check its parent, which is D. Next, we check the parent of D, which is A. Finally, we check the parent of A, and since the parent of A is A itself, we conclude that A is the root. Here, you may have noticed that we had to traverse the tree a bit more than in the earlier example to find the root. So, whenever we find the root of a tree that is not the parent of the node we are searching for, we simply connect that node directly to the root, making it the parent. This way, we save time when performing the operation on the same node again in the future. This technique is known as path compression. The time complexity of Kruskal's algorithm primarily depends on sorting the edges and detecting cycles. Sorting all the edges takes big O of E log E, where E is the number of edges. Cycle detection takes big O of alpha of V, where V is the number of vertices, and alpha is the inverse Ackermann function. You can look up the inverse Ackermann function on your own. In practice, its value is extremely small, so the term big O of E log E is the dominant factor. Now, talking about space complexity. The graph is represented using an adjacency list, which takes big O of V plus E space, where V is the number of vertices and E is the number of edges. Storing all the edges after sorting takes big O of E space. The parent table takes big O of V, and the rank table also takes big O of V. So ultimately, the total space complexity is big O of V plus E. Now, let's take a look at the Python implementation of this algorithm. You can skip this part if you're not interested in seeing the code. We will start by defining the disjoint set class. In the constructor, we will initialize the parent and rank tables. Now, the find method will take a vertex as input to determine its root. If the vertex is not its own parent, we will recursively call the find method on its parent and assign the result to the parent of the current vertex. This process is known as path compression. If the vertex is its own parent, we simply return it. Next, the union method will take two elements as input, on which the union operation is to be performed. It will then compare the ranks of these elements. The element with the greater rank will be made the parent of the other. If the ranks are the same, either one can be made the parent, and the rank of the new parent will be incremented by 1. Next, we will define the function Kruskal, which takes the graph as input. Inside this function, we will create a list called edges to store all the edges of the graph. We will then extract all the edges into this list and sort them in ascending order by their weights. Next, we initialize the vertices of the graph by converting the keys of the graph into a list. Then, we create an instance of the disjoint set class using these vertices. We also initialize an empty list called MST, which will store the edges of the minimum spanning tree. After that, we iterate through all the edges. For each edge, we extract the two vertices, U and V, and the weight of the edge. We then find the roots of U and V, using the find method of the disjoint set. If the roots of U and V are different, it means adding this edge will not form a cycle. So, we add this edge to the MST list and perform a union operation on the roots of U and V. Finally, we return the MST, which contains the edges of the minimum spanning tree. Now, if we run this code on our example graph, we should get the desired output, the edges of the minimum spanning tree.
Let's dive into how Dijkstra's algorithm works to find the shortest path in a graph. Here, we have a graph with 7 nodes, each connected by edges with specific weights. First, we need to initialize a table to track our progress. In this table, the first column lists the nodes. The second column represents the cost, or shortest distance required to reach each node from our starting point. Finally, the third column shows the previous node in the shortest path, helping us trace the route from the starting point to each node. Now let's set node A as our starting point. Initially, we'll set the distance to A as 0 since we're starting from there, and we'll mark all other nodes with infinity to indicate that they are currently unreachable. Now, we will initialize a priority queue where the element with the minimum cost will have the highest priority. Initially, the queue will contain only one node, the starting node. Then, we will start the algorithm. A loop will run as long as the priority queue is not empty. Inside this loop, we will pop the top element of the queue and check all of its neighbors. First, we pop node A and inspect its neighbors. Let's start by visiting node F. Note that you can visit the neighbors in any order. It doesn't matter. To calculate the cost of reaching node F, we add the cost of the current node to the cost of reaching the neighbor from the current node. In this case, the cost of A is 0, and the cost of reaching F from A is 3. Adding these gives us a total cost of 3 to reach node F. Next, we compare this calculated value with the current cost of F in the table. Since 3 is less than infinity, we update the cost of F to 3 in the table and set the previous node for F to A, as it was reached via A. Finally, we add this newly visited node F to the queue along with its updated cost. Then, we proceed to the next neighbor. Here, the cost of reaching B is 2, which is less than infinity. So we will update it to 2 and set the previous node to A. Then we will push this newly updated node into the queue along with the cost as the priority and proceed to the next neighbor. Now, the cost to reach node D is 5, which is less than infinity. So we will update it to 5, set the previous node to A, and then push node D into the priority queue along with the cost. Now that all the neighbors of node A have been visited, we need to proceed to another node. To do this, we will pop elements from the priority queue. Since B has the highest priority, i.e. the lowest cost, we will pop it and visit all its neighbors, just like we did with node A, updating the costs and previous nodes in the table if we find any shorter paths. Here, the cost of reaching node F via B is 6, which is more than the cost of reaching it via A, so there is no need to update this. Similarly, node A is already at the shortest path, so there is no need to update it. Now, getting to node E via B costs 3, which is less than infinity, so we will update it, set the previous node to B, and push E onto the priority queue with priority 3. Similarly, the cost to reach C via B is 9, which is less than infinity. So we will update it to 9, set the previous node to B, and insert C into the queue along with the cost. Now, all the neighbors of node B have been visited, and we need to go to another node. So we will pop the next element. Here, both nodes E and F have the same priority of 3, and which one to choose really depends on how the priority queue is implemented. Let's remove node E from the queue and visit all of its neighbors. Let's visit this node G first. Remember, the order of visiting neighbors does not matter. Here, the cost of reaching G via E is 6, which is less than infinity. So we will update it to 6, set the previous node to E, and add G to the queue along with the cost. Next, let's visit node D. This one is interesting because the cost to reach here via E is 4, which is less than the earlier cost of 5. So we will update the new cost to 4 and also update the previous node to E. Now we also need to update the cost of it inside the already inserted element in the priority queue. To do this, we will find that element and change the cost from 5 to 4. This process is called decrease key. Now, the time complexity of this decrease key operation really depends on the type of data structure used to implement the priority queue. If it is implemented using a binary heap, the operation will have a logarithmic time complexity. However, if it is implemented using a Fibonacci heap, the amortized cost of this operation can be constant time. Now, the algorithm will continue working similarly for all the nodes, visiting them one by one, checking all their neighbors and updating the table if necessary. I will pause the voiceover here until the queue becomes empty and the algorithm stops. Now that the priority queue is empty, the algorithm will stop here. Using the table, we can now find the shortest path from node A to any other node. Imagine we have to find the shortest path from A to C. First, we will check the previous node of C in the table, which is node E, so we will add node E. Then we check the previous node of E, which is node B, so we will add node B. Finally, we check the previous node of B, which is node A, so we will add node A. This sequence gives us the shortest path from node A to C. Now, the time complexity of this algorithm depends on the type of data structure used to implement the priority queue. In the most efficient case, a Fibonacci heap is used. Here, insertion into the queue is a constant time operation, and it happens V times, where V is the number of nodes or vertices, so the total time for insertion is big O of V. The initialization of the table also takes big O of V. Extracting the minimum from the priority queue is a big O of log V operation, and it happens V times, contributing big O of V log V. Finally, the decrease key operation, which is a constant time operation in a Fibonacci heap, can happen at most E times, where E is the number of edges. So the overall time complexity of the algorithm is big O of E plus V log V. Now, the algorithm requires space for the priority queue, which takes big O of v, and for the table, which also takes big O of v. Hence, the overall space complexity will be big O of v. Now, if the priority queue is implemented using binary heaps, the time complexity may degrade to big O of e plus v log v due to the less efficient insertion and decrease key operations compared to a Fibonacci heap. Now let's implement this algorithm using Python. If you prefer, you can skip this part if you're not interested in the code. First, we import the heap queue library to implement the priority queue. This library uses a binary heap, which is a simple and effective way to manage the priority queue in our algorithm. However, it's not as efficient as some other options, like Fibonacci heaps, particularly when dealing with operations like decreasing keys. But it's easier to implement in the code, making it a practical choice for this example. Next, we define the function Dijkstra, which takes the graph and the starting node as input. We begin by initializing the cost dictionary. For each node, we set the initial cost to infinity, except for the start node, which is set to 0 since it's the starting point. This allows us to track the shortest known cost to reach each node as the algorithm progresses. Then, we create the priority queue, which helps us select the node with the smallest tentative cost at each step. Now, a while loop will run as long as the priority queue is not empty. Then, we pop the elements and costs from the queue. We check if the current cost is more than the cost present in the table. If it is, we skip the iteration. Otherwise, we start visiting the neighbors and calculate the cost by adding the current cost to the weight of the edge. If the new cost is less than the cost in the table, we update it and push the current element back into the priority queue along with the updated cost. Finally, we return the cost table, which contains the shortest costs to reach each node from the starting point. Let's see how the Bellman-Ford algorithm finds the shortest path in a graph. It's similar to Dijkstra's algorithm, but with one key difference. Bellman-Ford can handle graphs with negative edge weights, and it can also detect negative weight cycles. First, we initialize a table to store information about the cost and the previous nodes. Initially, we set the cost to reach the source node to 0, while the cost of all other nodes is set to infinity. The previous field of all nodes is set to none. Next, we update the costs, also called relaxation. For each edge from node U to node V with weight W, we check if the cost to reach node U plus weight W is less than the current cost to reach node V. If it is, we update the cost of node V to this smaller value, and we also set the previous node of node V to node U, indicating that node U is the previous node in the shortest path. We repeat this for all edges, and we do this V minus 1 times, where V is the number of nodes. Next, once we've finished the relaxation process, we perform it one more time. If the costs are still being updated, it means the graph contains negative weight cycles. In this case, the algorithm fails. The reason for this failure will be discussed later in the video. And lastly, if there is no negative weight cycle, we are left with the shortest path from the source to all other nodes. Now, coming to our example, let's first initialize the table. We'll consider node A as our source node. So we set the cost of node A to 0 as it's already there, and then set the cost to all the other nodes to infinity. The previous node for all nodes is set to none. Now, since the total number of nodes is 7, we need to check this algorithm for at most 6 times, which is v minus 1, where v is the number of nodes. Next, we have to perform the relaxation of the edges. For each edge, the order in which we check them does not matter. The algorithm will give the same result. Let's start with the first edge in our order, the edge AF. The cost of node A is 0, and the weight of the edge is 3, giving a total of 3. This is less than the current cost of node F, which is infinity. So we update the cost of node F to 3 and set node A as the previous node for node F. Next, for the edge AB, the cost of node A is 0, and the edge weight is 2. Combining both, we get a total of 2, which is less than the current cost of node B. So we update the cost of node B to 2 and set node A as the previous node for node B. Similarly, the cost to reach node D is 5, which is less than the current cost. So we update the cost of node D to 5 and set node A as the previous node for node D. Next, for the edge BE, the cost of node B is 2, and the weight of the edge is 1, giving a total of 3. This is less than the current cost of node E, so we update the cost of node E to 3 and set node B as the previous node for node E. Next, for the edge DE, the cost of node D is 5, and the weight of the edge is 1, giving a total of 6. This is not less than the current cost of node E, so there's no need to update the cost. Next, for the edge EC, the cost of node E is 3, and the weight of the edge is -3, giving a total of 0. This is less than the current cost of node C, so we update the cost of node C to 0 and set node E as the previous node for node C. Next, for the edge EG, the cost of node E is 3, and the weight of the edge is 3, giving a total of 6. This is less than the current cost of node G, so we update the cost of node G to 6 and set node E as the previous node for node G. Next, for the edge CB, the cost of node C is 0, and the weight of the edge is 7, giving a total of 7. This is not less than the current cost of node B, so we will not update it. Next, for the edge CG, the cost of node C is 0, and the weight of the edge is 4, giving a total of 4. This is less than the current cost of node G, so we update the cost of node G to 4 and set node C as the previous node for node G. Next, for the edge GD, the cost of node G is 4 and the weight of the edge is -1, giving a total of 3. This is less than the current cost of D, so we update the cost of node D to 3 and set node G as the previous node for node D. Next, for the edge FB, the cost of node F is 3, and the weight of the edge is -4, giving a total of -1. This is less than the current cost of node B, so we update the cost of node B to -1 and set node F as the previous node for node B. Now the first iteration is over, so we proceed to the next iteration. This time, I will stop the voiceover until the next iteration, as the steps are exactly the same as before. Observe the relaxation carefully. Now, the second iteration is over, so we proceed to the third iteration. Observe this one carefully, as there is an important concept to cover after this iteration. In this iteration, no further updates occur. This means there won't be any more relaxations in the later iterations, and no updates during the negative weight cycle detection either, so there's no need to check further. We can stop here and return the results. Now let's use this result to find the shortest path from node A to node G. First, we check the previous node of node G, which is node C. So we add node C to the path, and then check its previous node, which is node E. We add node E to the path and look at its previous node, which is node B. Next, we add node B to the path and check its previous node, which is node F. We add node F to the path and then check its previous node, which is node A, the source node. Since we've reached the source, we stop here. Now, we have the shortest path from node A to node G. Now, let's understand the key issue with negative weight cycles. So here, we have a graph with nodes A, B, and C, and it contains a negative weight cycle, meaning the sum of the weights of the edges in this cycle is negative. Let's perform the same algorithm on this graph using node A as the source node. We will initialize the cost of node A to 0 and set the cost of all other nodes to infinity. Additionally, the previous node for all nodes will be set to none. Now, since there are a total of 3 nodes, we need to perform the relaxation process 2 times, and then check for negative weight cycles. First is the edge AB. The cost of node A is 0 and the edge weight is 1, giving a total of 1. This is less than the current cost of node B, so we update the cost of node B to 1 and set node A as its previous node. Next is the edge BC. The cost of node B is 1 and the edge weight is -4, giving a total of -3. This is less than the current cost of node C, so we update the cost of node C to -3 and set node B as its previous node. Next is the edge CA. The cost of node C is -3 and the edge weight is 2, giving a total of -1. This is less than the current cost of node A, so we update the cost of node A to -1 and set node C as its previous node. Now, the first iteration is over, and we will perform the second iteration in a similar manner. The main reason the algorithm fails in the presence of negative weight cycles is that it keeps finding smaller and smaller paths indefinitely. It will continue converging to lower and lower costs forever, without ever stabilizing. The second iteration is now complete. Next, we perform one more iteration to confirm whether there is a negative weight cycle. If such a cycle exists, the algorithm will continue updating the costs. Now, here the current cost of node A is -2 and the edge weight is 1, giving a total of -1. This is less than the current cost of node B, indicating that updates are still occurring, which shouldn't happen if there were no negative weight cycle. This confirms the presence of a negative weight cycle, causing the algorithm to fail at this point. Now the algorithm goes through all the edges v-1 times to perform relaxation and one more time to check for negative weight cycles, so the total time complexity is O of v times e. The algorithm uses space to keep track of the costs and previous node information, which depends on the number of nodes. It also needs space to store the graph, which is proportional to the number of nodes and edges. So the total space complexity is O of v plus e. Now, let's take a look at the Python code implementation of this algorithm. If you're not interested, feel free to skip this part. First, we define a function that takes the graph and the source node as input. Then, we initialize a table where the cost of all nodes is set to infinity, and the previous node for each is set to none. Next, we mark the cost of the source node as 0. Next, we initialize a variable called relaxation and set it to false initially. This variable will help us track whether we need to continue the relaxation process or not. Then, we run a loop for 1 less than the number of nodes in the graph to perform the edge relaxation process. Next, we go through each edge pair in the graph and perform the relaxation process as discussed earlier. If a relaxation occurs, we also set the relaxation variable to true. And then, if no relaxation occurred in the previous iteration, we simply break the loop here. And if relaxation occurred, we check for the negative weight cycle. If there is one, we simply indicate that the algorithm has failed and return from there. And if there is no negative weight cycle, we simply return the table with the final costs and previous nodes. For the full implementation of the algorithm, check out the GitHub link below.
Let's understand how the Floyd-Warshall algorithm finds the shortest path between any two pairs of nodes in a graph. Earlier, we've seen single-source shortest path algorithms like Dijkstra's and Bellman-Ford. If you're not familiar with those, I suggest checking them out first, as they provide a solid foundation for understanding shortest path algorithms. Those algorithms are designed to find the shortest path from a single source node to all the other nodes. For example, from node A to all the other nodes in the graph. But what if we want to find the shortest path between all pairs of nodes? One approach could be to run those single-source algorithms on each node once. However, this method can be inefficient, and that's where the Floyd-Warshall algorithm comes to the rescue. This algorithm operates on the adjacency matrix of the graph, where each entry represents the weight of the edge between two nodes. If no direct edge exists, the entry is set to infinity. Now let's name this matrix M0, and we need to initialize another matrix, T0, known as the predecessor matrix. This matrix keeps track of the previous nodes in the shortest paths and will be used to construct the shortest path between any two nodes. The core idea here is to systematically visit each node and check if it can act as an intermediate point to provide a shorter path between any two nodes. If such a path exists, we update the matrices accordingly. This process is repeated for all nodes in the graph. Let's find the next matrices in the following iteration. Keep in mind, the matrices shown below are purely for demonstration purposes. In reality, only one instance of these matrices exists and gets updated dynamically. This visual breakdown is just to help you understand how the algorithm works. Let's start finding shorter paths via node A first. The rows and columns connected to A will not be updated because they already represent the direct connections. Additionally, the diagonal elements will remain unchanged, as updating them would imply the presence of a negative weight cycle. If you're unfamiliar with negative weight cycles, I recommend checking out our video on the Bellman-Ford algorithm for a detailed explanation. Now, let's see how the updation works. First, let's check the path from B to C. The current cost for this path is 2. We'll check if a shorter path exists via node A. First, going from B to ACE, there is an edge with a weight of 3. Next, we check the cost of going from A to C, which is infinity, meaning there is no path from A to C. Since there's no shorter path through node A, the previous edge with a weight of 2 remains the shortest path. Next, let's check the path between B and D. The current shortest cost to reach D from B is infinity, meaning there's no direct path. We'll check if a shorter path exists via node A. First, the path from B to A has a cost of 3, and the path from A to D has a cost of 3. Adding these, the total cost becomes 6, which is less than the current shortest path of infinity. Therefore, we update the cost to 6 and set the previous node to A, as the path to D goes through A. Next is the path between C and B. The current shortest cost to reach B from C is infinity, meaning there's no direct path. We'll check if a shorter path exists via node A. First, the path from C to A has a cost of infinity, meaning there's no path yet, and the path from A to B has a cost of 2. However, the total still remains infinity, so we won't update this one. Next is the path between C and D. The current shortest path has a cost of 4. The path from C to A has a cost of infinity, and from A to D is 3. Since this is more than the current cost of 4, we will not update it. Next is the path between D and B. The current shortest path has a cost of 6. However, if we go via A, the cost from D to A is -2, and from A to B is 2, giving a total of 0, which is less than the current cost. So we update it to 0 and set the previous node to A, since the path is coming via A. Next is the path from D to C. Currently, the shortest path has a cost of infinity. If we look via A, the cost of going from D to A is -2, and from A to C is infinity, meaning there is no path yet, so we will not update it. Now the first iteration is finished. Let's name this new updated matrix as M1, and the updated predecessor matrix as T1. In the next iterations, we will check if we can reduce the costs further by going through other nodes. Since we've already checked node A, let's now see whether we can get shorter paths via node B. And just like the previous iteration, we will not be updating the rows and column of B, as they already represent the direct connections. Also, we will not check the diagonal element, since our example graph does not have negative weight cycles. Now let's see the path between A and C. Currently, the cost to reach there is infinity, meaning no path is known. But if we look via B, first, going from A to B has a path with a cost of 2, and going from B to C also has a path that costs 2, giving a total of 4. Since 4 is less than infinity, we will update it to 4 and set the previous node to B, as the path is coming via B. Next is the path between A and D. Currently, the shortest cost is 3, but if we check via B, the cost from A to B is 2, and the cost from B to D is 6. This gives a total of 8, which is more than the current cost of 3. So we will not update this one. And similarly, we will perform the updates. Try pausing the video and solving it yourself. You should get these updated values. Now, this is the matrix M2 and T2. Similarly, we will find the matrices M3 and T3 via node C in the next iteration, and then the matrices M4 and T4 via node D. And once we check the shorter paths via all the nodes, we will stop. Now, we can use these final updated matrices to construct the shortest path from any pair of nodes. Now, let's construct the path from node C to B. Here in the matrix, we can see that the shortest path has a cost of 4. But to actually construct it, we need to look at the previous node in the predecessor matrix, which is node A. So we will add A to the path. Next, we need to find the previous node in the path from C to A, which is D. So we will add D now. Now, this is our shortest path from C to B. This is how to construct the shortest path between any pair of nodes. Now, the algorithm loops over each node once and traverses the whole matrix for each node. So the time complexity is big O of V cube, where V is the number of nodes. And the space complexity is big O of V square, as we use matrices to store the shortest paths and predecessor information. Now, let's see the Python code implementation. Feel free to skip this part if you're not interested. First, we will import the math library. Then, we will define a function that takes the dimension n and the matrix as input parameters. Then, we initialize a variable infinity using the math library we imported earlier. Next, we initialize the previous node matrix with none values. Then, we also create a variable nodes that maps indices to letters like A, B, C, and so on. After that, we loop over the distance matrix, and for each pair of nodes, if there's a direct edge between them, we set the previous node in the previous node matrix to the source node. We then run a loop n times, where n is the number of nodes. In each iteration, we traverse the entire matrix once, and at each element, we check if there is a shorter path. If a shorter path is found, we update both the distance and the previous node matrices. We then loop over the diagonal elements of the resultant distance matrix and check if any element is less than 0. If there is, we indicate that the algorithm fails due to the presence of a negative weight cycle and return none. Otherwise, we return the distance and previous node matrices. Check out the GitHub link in the description box for the complete code.
In this video, we will discuss some popular sorting algorithms. Let's start with bubble sort. Bubble sort works by repeatedly stepping through the list, comparing adjacent elements, and swapping them if they are in the wrong order. If the element on the right is smaller than the one on the left, we swap them. This process is repeated for each pair of adjacent elements, effectively bubbling the largest unsorted element to its correct position at the end of the list. The process continues until no more swaps are needed, indicating that the list is fully sorted. Now imagine if the list is already sorted. In this case, the algorithm will simply traverse the list once, comparing adjacent elements. Since all elements are already in the correct order, no swapping will occur. Bubble sort is optimized to stop early in such scenarios, as it can detect when the list is sorted and terminate, making it more efficient in this particular case. Now let's go through the Python code for bubble sort. First, we define a function that takes the array as an input parameter. We store the length of the array in the variable n. The algorithm uses a loop that runs n times. Inside this loop, we use a variable called swapped to keep track of whether any swapping has occurred during the current pass. We then use a nested loop that runs from the beginning of the array to the last unsorted position. Pause this video and put some pressure on your brain to understand why the loop runs to n-i-1. Within this loop, we compare each pair of adjacent elements. If the previous element is greater than the next element, we swap them and set the swapped variable to true to indicate that a swap has occurred. After the nested loop completes, we check the swapped variable. If no swaps were made, we break out of the outer loop early, as this indicates that the array is already sorted and no further passes are needed. The time complexity will be big O of n square in the average case, because it involves two nested loops, the outer loop for each pass and the inner loop for comparing and swapping adjacent elements. However, in the best case, when the array is already sorted, the algorithm only needs to traverse the list once without making any swaps. So the complexity in this scenario will be linear. The space complexity is constant because bubble sort sorts the array in place and does not require any additional space beyond a few variables. The next algorithm is insertion sort. We start by assuming that the first element is already sorted. Then we take each subsequent element from the unsorted portion of the list and insert it into its correct position within the sorted portion. For each element, we compare it with the elements in the sorted portion and shift the larger elements to the right to make space. If the array is already sorted, the algorithm will simply traverse the list without making any insertions or shifts. Now let's see the code for this. First, we define the function with the array as the input parameter. We run a loop from the second element to the end, assuming the first element is already sorted. Inside the loop, we initialize a variable key to hold the current element, and a variable j to represent the last index of the sorted portion of the array. We then use a while loop with the condition that j is greater than or equal to 0, and the key is less than the element at index j. Within this loop, we assign the element at j to the next position, j plus 1, and then decrement j. This process effectively shifts the elements to the right. After the while loop, we assign the key to the j plus 1 element, placing it in its correct position. This ensures the current element is inserted into the sorted portion of the array. The time complexity of insertion, sort in the best case, when the array is already sorted, is linear because no shifting is required and the inner loop does not run. However, in the average and worst cases, the time complexity is big O of n square due to the shifting of elements. In these cases, both nested loops run, resulting in more comparisons and shifts. The space complexity is constant because the algorithm sorts the array in place and does not require extra space beyond a few variables. Next is the selection sort. This algorithm is quite simple. It starts by finding the smallest element in the entire list and swapping it with the element in the first position. Then, it finds the smallest element in the remaining unsorted portion and swaps it with the element in the second position. This process continues, gradually expanding the sorted portion of the list while shrinking the unsorted portion. Now let's look at the code for selection sort. It starts by defining a function that takes the unsorted array as input. We then create a variable n to hold the length of the array. A for loop runs n times to process each element. Within the loop, we initialize a variable min index to keep track of the index of the minimum value found in the unsorted portion of the array. An inner loop runs from the beginning of the unsorted portion to the end, comparing each element with the element at the current min index. If a smaller element is found, the min index is updated. After the inner loop finishes, we swap the element at the current position with the element at min index, placing the smallest element in its correct position. This process continues until the entire array is sorted. Finally, the function returns the sorted array. Despite its simplicity, selection sort has a time complexity of big O of n square, in all cases, because it involves nested loops to find the minimum element and perform swaps. However, its space complexity is constant time, as it sorts the array in place without needing extra memory beyond a few variables. Next, we'll discuss merge sort. But before we dive into visualizing the sorting process, it's important to understand how merging two sorted lists works to ensure that the resultant array remains sorted. Let's first look at the code for merging two sorted lists. First, we define the function merge that takes two sorted arrays, left and right, as input parameters. We then initialize a new array called result, which has a size equal to the sum of the sizes of both input arrays. Next, we create two variables, I and j, both initially set to 0. These will be used to keep track of our position in the left and right arrays, respectively. We run a while loop with the condition that I is less than the length of the left array and j is less than the length of the right array. Inside this loop, we compare the element at index I of the left array with the element at index j of the right array. If the element in the left array is less than or equal to the element in the right array, we append the element from the left array to the result array and increment I by 1. Otherwise, we append the element from the right array to the result array and increment j by 1. After the loop ends, one of the arrays will be exhausted while the other still has remaining elements. We then extend the result array with the remaining elements from whichever array still has elements left. Finally, we return the result array, which now contains all elements from both input arrays merged and sorted. The time complexity of the merge operation is linear because it involves a single loop that processes each element of the two input arrays exactly once. The space complexity of the merge operation is also linear because we need to allocate additional space for the result array that holds the merged elements. This extra space is proportional to the size of the input arrays, making the space complexity linear. Now, let's see this visually. Imagine we have two sorted arrays, array 1 and array 2. The algorithm will first create a new array to hold the merged result. It will then initialize two pointers, I and j, to track the current index of each respective array. As the algorithm compares the elements at these indices, it will copy the smaller element into the new array and increment the corresponding pointer by 1. This process continues until one of the arrays is fully traversed. Once that happens, the algorithm will extend the new array by appending any leftover elements from the other array. This ensures that all elements are included in the final sorted array. Now let's perform merge sort. This algorithm works by recursively dividing the array into two halves until each subarray contains only one element, which represents the base case. In our visual representation, we will use a light bluish color to indicate these base case elements. If the array has an odd length, we split it such that one half has one more element than the other. Once we reach the base case with individual elements, the algorithm starts merging them back together in a bottom-up approach using the merge function we've defined earlier. This process combines the individual elements into sorted pairs, then sorted quarters, and so on, until we finally obtain a fully sorted array. The code for merge sort is straightforward. First, we define the function merge sort, which takes an unsorted array as the input parameter. The base case of the recursion is when the length of the array is less than or equal to 1, meaning the array is already sorted. Next, we calculate the midpoint of the array by dividing its length by 2. We then recursively apply the merge sort function to both halves of the array, storing the results in the left and right variables. Finally, we merge these sorted halves together using the merge function and return the merged array. The number of divisions of the array is proportional to the logarithm of the number of elements. During each level of division, we merge pairs of sorted arrays, which takes linear time. So, the overall time complexity will be big O of n log n. Now, the merging of arrays requires big O of n space, and the depth of recursion is log n. But the dominant term is n, so the overall space complexity would be big O of n. Next is the quicksort algorithm. Before performing sorting first, we need to see how a partition algorithm works. Let's walk through the code for the partition function first, which is a key part of the quicksort algorithm. First, we define the function partition, which takes the array R, a starting index low, and an ending index high as input parameters. The pivot element is chosen as the element at the high index of the array. This pivot element can actually be selected in various ways. In this example, we picked the last element, but you could choose the first element, the middle element, or even a random element from the array. The choice of the pivot can impact the performance of the quicksort algorithm. We then initialize a variable I to low -1, which will track the position where the smaller elements than the pivot will be placed. Next, a for loop runs from the low index to the high -1 index. In this loop, we compare each element in the array with the pivot. If an element is smaller than or equal to the pivot, we increment the index I and swap the element at position I with the current element at position j. This ensures that all elements smaller than or equal to the pivot are on the left side. After the loop completes, we swap the element at position I plus 1 with the pivot element, placing the pivot in its correct sorted position. The function then returns the index I plus 1, which is the final position of the pivot element. Now let's see the visuals in action. First, we choose the pivot element, which in our case is the last element of the array. Next, we initialize two variables, j, which starts at the first element of the array, and I, which is initially set just before j. As we iterate through the array, we compare whether the element at index j is less than or equal to the pivot. If it is, we increment I by 1 and swap the elements at index I and index j. This process continues until j reaches the end of the array. Finally, we swap the pivot element with the element at the I plus 1 position, placing the pivot in its correct sorted position. This process essentially creates a partition. All elements smaller than the pivot are moved to the left of the pivot, while the larger elements are positioned on the right. The pivot now sits in its correct sorted place within the array. Note that the elements to the left and right of the pivot don't need to be in any specific order at this point. The partitioning step only ensures that all smaller elements are on the left and all larger elements are on the right, but they aren't necessarily sorted within their respective sides yet. Now, let's perform quicksort using this partitioning method. First, we'll partition the array, starting with the last element as the pivot, arranging all the smaller elements to its left and the larger ones to its right. Then, we recursively apply the same partitioning process to both the left and right subarrays until each subarray contains only one element, which is the base case, meaning the array is sorted. At the end of this process, we obtain a fully sorted array. Now, in the best and average cases, the depth of recursion will be proportional to the logarithm of the number of elements. This happens because the array is split roughly in half at each step. Since it takes big O of n time to partition the arrays at each level, the overall time complexity becomes big O of n log n. The space complexity depends on the depth of recursion. So in the best and average cases, it is big O of log n, due to the balanced divisions of the array. However, the worst case scenario happens when the pivot selected is either the smallest or the largest element in the array. This leads to highly unbalanced splits, with one side having almost all the elements. In this example case, the array is already sorted, and the pivot is also the last element, meaning it will be the largest in every case. This results in a recursion depth of n rather than log n, as the partitioning is not balanced. As a result, the time complexity in the worst case becomes big O of n square, and the space complexity also increases to big O of n. Now the code for quicksort is pretty simple. First, we define the quicksort function, which takes the input array and two parameters, low and high, representing the starting and ending indices of the current portion of the array. The base condition for recursion is when low is less than high, meaning there is more than one element in this portion to sort. If this condition is false, the recursion stops. Inside the recursive call, we invoke the partition function, which rearranges the elements in such a way that all smaller elements are to the left of the pivot, and larger ones to the right. It returns the index of the pivot, which is now in its correct position. After partitioning, we recursively apply quicksort to the subarrays on the left and right of the pivot. This is a summary of the time and space complexities for all the sorting algorithms we've discussed. In the table, the columns labeled best, average, and worst represent the time complexities for each scenario. The space column indicates the space complexity for the algorithms. It's important to note that the space complexity remains consistent across all algorithms in all situations, except for quicksort, which can vary depending on the situation. Knuth-Morris-Pratt Algorithm, or KMP algorithm, is an efficient pattern matching algorithm used to find instances of a pattern within a given text. But before moving on to the KMP algorithm, let's first take a look at how a naive pattern matching algorithm works. First, we'll slide the pattern over the text and start comparing the corresponding elements one by one. If all the elements of the pattern match, we'll note the index of the match. However, if any one element mismatches, we'll move the pattern one step forward and repeat the process. In this naive approach, the pattern slides over the text n minus m plus 1 times, where n is the length of the text and m is the length of the pattern. In each pass, it compares on average half the length of the pattern. So the final time complexity will be big O of m times n. And the space complexity is constant because the algorithm doesn't require any additional data structures beyond the pattern and the text themselves. Now, coming back to the KMP algorithm. Before we proceed with the search, we first need to construct the longest prefix-suffix array, or the LPS array. This array is the same size as the pattern, and the idea here is that if a suffix of the pattern matches a prefix, we can avoid rechecking those characters when a mismatch occurs. In this pattern, the first letter A does not have any prefix or suffix, so the value in the LPS table for this position will be 0. B also doesn't have any matching prefix, so its position in the LPS table will also be 0. Now the next A does have a matching prefix, which is the first letter A, so its value in the LPS table will be 1. Next, the character B also has a matching prefix, which is the second character B, so its value in the LPS table will be 2. Similarly, we will check the prefix-suffix relationships for all the subsequent elements in the pattern and fill in the LPS table accordingly. Now that we understand the intuition behind the LPS table, let's go through the steps of constructing it. We will initialize an array with the same size as the pattern and set all of its elements to 0. We initialize two variables, I set to 1 and L set to 0. We then enter a loop where we compare the pattern elements at the current positions of I and L. If the characters don't match and L is not 0, we update L to the element at L minus 1 index in the LPS array. If L is 0 and there's no match, we just increment I by 1. If the characters match, we increment L by 1. We set the elements at the I index in the LPS array to L. Then we increment I by 1. Then we continue the loop until I reaches the length of the pattern. Now, once we obtain the LPS array, we can move on to the searching phase. First, we initialize two pointers, I and j, both initially set to 0. Then, we start matching the pattern element at the j index with the text element at the I index. If they don't match, and j is not 0, then we update j to the element at j-1 index in the LPS array. And if j is 0, then we simply increment I by 1. And if the elements match, we increment both I and j by 1, and continue. Now, it mismatches again, and in this case, j is not 0. So, we will update j to the value at j-1 index in the LPS table, and continue. Now, observe how the algorithm avoids rechecking the elements that have already been matched in the prefix. This is how the KMP algorithm efficiently handles pattern matching, by using the LPS table to skip unnecessary comparisons and avoid rechecking matched prefixes. And also observe that the pointer I is not backtracking, which shows that the algorithm operates in linear time. And if a match is found, print its index in the text, then update j to the value at j-1 index in the LPS array to continue searching for further instances of the pattern. Upon reaching the end of the text, the loop breaks and the algorithm stops. Now, the time complexity of the algorithm depends on two parts. The first is the construction of the LPS array, which involves looping over the pattern once, so the time complexity of that is big O of m, where m is the length of the pattern. The second part is the searching phase, which involves looping over the text, which has a time complexity of big O of n, where n is the length of the text. Therefore, the total time complexity of the KMP algorithm is big O of m plus n. Additionally, the algorithm requires an array to store the LPS table, which has a size equal to the length of the pattern. This means the space complexity is big O of m, where m is the length of the pattern. Since we only need this array and a few extra variables, the overall space complexity remains big O of m. Before talking about Rabin-Karp algorithm, let's see how the naive algorithm to solve the same problem works. We will slide the pattern over the text and match the corresponding letters in each iteration. And if a match is found, we will note its index. The time complexity of this approach is big O of n minus m plus 1 times m divided by 2. Here the pattern travels n minus m plus 1 times over the text, and in each iteration, on an average, it compares m divided by 2 characters. Simplifying this will give the complexity big O of n times m. Now, Rabin-Karp algorithm solves this problem much more efficiently. Before going into the algorithm, we must understand the concept of rolling hash function. So here is the formula to calculate the initial hash value. Here, the C values represent the ASCII code of the characters. And B is the base of the code system, 256 in our case, and N is the total number of characters. And P is a large prime number. We first calculate the hash value and then just update it using this formula. Here, the HOLD is the initial hash value that we have calculated. We will just subtract the contribution of the last character and add the contribution from the next character to calculate the new hash value in constant time. So, taking 101 as the prime number, we first calculate the initial hash value in linear time complexity, and then roll it over the text to find the other hash values by just updating the hash value in constant time. Here we are removing the leftmost contribution and adding the rightmost contribution while updating. So, what the Rabin-Karp algorithm does is that it compares the hash value of the pattern and the hash value of the sliding window. It only starts matching the corresponding characters if the hash value matches. This character matching is to cross-verify that it is indeed the actual pattern, not a hash collision, also called a spurious hit. By doing this, we avoid unnecessary comparisons. It takes big O of n minus m plus 1 times for the pattern to slide over the text and big O of m to calculate the initial hash value. So, the average time complexity would be big O of n plus m. Now in the worst case, imagine if the hash value of each window is the same as the pattern hash. It would have to cross-verify again and again, essentially making it as worse as the naive algorithm. So the algorithm depends on the robustness of the hash function used. In the worst case, the complexity is the same as the naive one, but on average, Rabin-Karp algorithm is usually a much efficient algorithm.